Great. Week sixth, not sixth, week sixth, day first. We'll talk about high throughput systems. Actually, it's not really high throughput. High throughput, it's extended to, it is an extension to storage. So what happened is earlier, first 3 or 4 cohorts I'm talking about, I used to cover S3 in storage week itself. So week 5 itself, we used to cover S3. But then I found like, hey, I should go a little more deeper into the way I'm the kind of things I'm covering, and because people are comfortable with those concepts. So that's where I moved S3 to this week, giving enough space for other discussions. So yeah, it's like over time the course has evolved really well. So the agenda for today is we'll design S3. That's huge. That is going to be a huge discussion, and which is where you understand that hey, the systems are not as simple as we think they are. And but yeah, that's the beauty of it. And we'll talk more about tiered storages, because I want to go really deep into tiered storages, because that is one of the most underrated way to get performance out of your system while keeping the cost down. Right. So we'll talk about S3 after half an hour. But before that, I'll just switch the order and cover a cost-efficient order storage system. Right? This is what we would start with first. This is where you get glimpse of data engineering, like quote unquote data engineering, and how those systems are built. And then we start with S3. We basically cover it to 25-30% on brainstorming. Then we take a break and then we cover complete S3, right? So around 11:30, 11:40 it would go. And then obviously open questions at the end, right? Okay, so before that, just want to touch upon bunch of continuous feedback that I got. Would request you to split out class to 2. 3-hour class at a time is very lengthy, unable to focus with the same energy till the end. I agree, but that's the beauty of it. I'll still think, because if I split it, it becomes way too short. Does not seem like we are actually covering decent enough. For example, if I cover that what was that real-time communication, that itself went for 2 hours 20 minutes, right? S3 will go for 2.5 hours, right? So splitting that would become way too small. But the way the courses evolved, I felt dismissed, but point taken. I'll try to see like if I can split something into 2. In those cases, I'll give longer breaks, like 10-15 minutes breaks, and we'll try to manage something. But point taken. It's hard. I can understand that totally. And can you please request viewers to not answer questions asked by you while discussing any topic in the chat box? It's not my control. It's fun to have like chat. So folks who are distracted by chat box, just stay away from it and brainstorm on your own. But it's fun when people post things on chat boxes, right? So I cannot stop that, because it would make things very monotonous. It's better, and in case you are someone who gets affected by seeing the prompted answers in the chat box, just keep the chat minimized, right? And when you feel like that, then open, because but take it like to each its own. But just keep your chat closed. There is an option to do that. This way it would work out well. Right? Okay. These were the 2. And yeah, one more I received last week, which I forgot to cover, is when are we going to have one-on-one? So I'll not schedule it. You have to schedule, because it's on demand. You have to schedule. So whoever wrote that question in feedback, please make a note. That link is there on Relog. Go and block my calendar for that. Right? Okay, great. Fine. Sure. Let's move to the technical side of things. Cost-efficient order storage system. So this is where for next half an hour, I'd want to talk about like why multi-tiered data stores are so important and how they come in really handy. So in most and why orders I'm taking as an example, because it fits this use case really well. So I touched upon fraction of it last week, but we'll go deeper into how a system like this is built and how you should build a system, right? And it's very much inspired from a lot of other systems that already exist. Something very similar I also worked on. So I can very closely relate to it. Okay, this is the kind of architecture that typically happens. Okay, so let's start with the first one. So transactional systems, you typically have like whenever you, let's say you're building an e-commerce system. In e-commerce system, you take orders. So you need to, when you take orders, you need to store orders somewhere. So that is where you say, let's say if you store those orders that are coming in a transactional database. Now, when these orders are being accepted, they are being stored in the transactional database. Now, what happens is other services need this order information. For example, your payment service needs this order information so that it can update its own status and basically collect payment and EMIs and whatnot flow. The logistics service needs this order information so as to know, okay, which order am I delivering? And it would update that corresponding entry in those databases. Okay, hey, because in the orders page, you see that, hey, you need this order. This is where it is at the stage of delivery, right? It's shipped, it's packaged, dispatched, shipped, out for delivery and whatnot, right? Then customer support also needs this order information in order to solve your queries, right? When you reach out to, let's say, Amazon customer support, they would have your order details. So a lot of systems are dependent on orders. But here, when a lot of systems are dependent on this one single subsystem, you realize that this system is not just handling end user request, but also request from other internal services. And then you say, okay, when I'm getting these many requests, scaling up API servers is fine. We all know, just put a load balancer, add more servers, define an auto scaling policy. Your API servers are stateless and it can very easily scale. Things become tricky because of database that you have. And you say, okay, now my database, I need to scale my database. So what do? You apply 3 very common ways to do it. First, you try to scale up. You try to vertically scale the database until a certain limit. Then you say, hey, I have large amount of reads, which is very much there because why would customer support write to your orders? It would not. It would only read from it, right? Logistics, why would it write? It would just read that which package am I delivering, right? Payments would also read. So you see a very high read traffic happening on your order service because of internal services that are coming in, right? Writes are typically from the customer side that are happening, right? Few writes internal also there, but you get the idea. You say, hey, let me just add read replica, right? Let me add read replica on my master database and I'll just transfer my reads to read replica. This way I would be able to scale the reads request that I'm happening. So that works well. Now what happens is, now you get even more, you're getting more orders, which means there are more write requests, which one node cannot handle, which one vertically scaled up node cannot handle. What do? You shard it, right? So you break your master into subsets or into n databases with n mutually exclusive subsets of data, right? For example, orders from user 1 to 100 over here, 100 to 200 over here, 200 to 300 over here. Let's say there are only 300 users. So you create mutually exclusive groups and shard it up, right? We saw this approaches far too many times up until now, right? But now when you do this, it's not always a good choice that you are doing it because you're now, it's little more complex sharding, especially when it comes to relational database. You have to typically manually shard the database and have your API server know where to forward the request to, right? So sharding is okay. You can still do it if you have good engineering team. But now think about it. I'm like, how long would you just keep on horizontally scaling the data, right? Because now after a certain point in time, you would have large number of these databases, unnecessarily large number of these databases. So what can you do? It's like, no, but after sharding, what else? What else can we do? The thing is, when you have, like, if you look closely at this stage of your database architecture, where you have read replicas, at this stage, you must figure out that this one database was not able to handle lot of write requests, which is where you were doing sharding. But now what you should look at over here is that what is the root cause of degradation? Why is your DB not able to handle the load? Okay. One crude optimization that you can do over here is, hey, whatever data I have in my database, am I accessing all of them? Do I need all of the data to be present in my main transactional database? This is the question that we need to ask, because now what happens is, let's say you have orders table. You have huge orders table. Let's say Amazon takes orders, let's say 100,000 orders per minute. And I'm not sure what the numbers are, but let's assume that 100,000 order per minute. So now what happens is your orders table will have huge number of entries. And when it has huge number of entries, then whatever you are querying on it, even though you have indexes, right? Huge table will have huge index. Huge index, you need to fit this huge index in memory. Now, which means that let's say if there are 10 million orders on Amazon and you created an index of the 10 million, that index of 10 million orders needs to be fit into memory. Otherwise, spill on the disk and whatnot would be there. When you have this much of data, are you actively querying all of the data? Not really. Because this is where what you see is degradation in performance because there is huge amount of data that you are putting into your database. Into this one node that you have, the amount of data that you are putting in is huge enough. Do you really need all of the data? This is a critical question that you should ask. Because in most cases, whenever you are storing any information, anywhere in the database, every single row, every single object has a life cycle to it. At some point in time, that object is accessed very frequently, and then the pattern deteriorates. Then it degrades. Then the amount of the number of accesses that would happen is much lesser than what they used to be. So every object in every system, literally every single system, has a life cycle to it. And the life cycle depends on the use case. In some cases, you would see that most recently posted stuff gets very high traction. After that, no one gives a damn about it, right? For example, you tweeted something, it's very likely that you would get very high traction during the first phase of it, like first 1 or 2 days, and then no one cares about it. So you see very less engagement into it, right? Similarly for orders, when the order is very fresh, you're doing a lot of reads and writes onto it, because just imagine the order is just placed. Immediately your payment service would be querying it. You might be just reaching out to customer support to get things done. Then your logistic would be constantly querying this to know what you're delivering, how you're doing, updating the database and what. So a lot of information would be getting read and updated when an order is newly created. But once your order is delivered, logistics is out of question, because logistics is done, right? The order is delivered. Now logistics has no reason to query your order service. So then this goes out of window. Payment is done. Payment is done in one or in 10 minutes. After that, payments also does not need to do anything. Then what happens is once your order is delivered, then for let's say 1 month, you have your warranty period, which is where you are likely to access, you are likely to call your customer support to get something. So that's where you would see only load from from the customer support team. And user, in case user is going through historical orders, right? But you see that in classic case of orders, there is a very high access that you're doing, reads and writes both, when order is very new. Before order gets delivered, you see a lot of frequent reads happening. After that, no one cares, right? If order is, let's say, 6 months old, no one cares on what's happening. I think I've made some order. Maybe during once a year, during your filing of taxes, you go through your orders and see, okay, this is huge amount of money that I spent, and you go under it. So every single system in the world, wherever you are storing this data, whatever data you are storing, try to understand the life cycle of the data. How frequently it is being used, when it is being used, when that access frequency drops. Now you'll say, but how do I know? First, metrics, right? You can either clock when a particular item is accessed, how frequently it is accessed, that. Otherwise, you can just guess, right? That also works. Like in case of orders, you can very easily guess that, hey, this is how this access pattern should be. But if you have it quantifiable metrics, good enough. If not, even a guess works fine. Right? This holds true for almost all systems out there. Social networks. How likely are you to access your Facebook post made in 2008? Very unlikely, right? How likely are you to access your own tweets that you made 1 month ago? Highly unlikely, right? Given that, it's very unlikely for you to access it. So which means that there would be an access pattern for anything, right? Now, obviously there are aberrations, there are anomalies in it, because there are cases where a historical post suddenly gets traction and it goes viral. Right? That is exception. But in most cases, for most people, like say 99.99% of cases, access pattern would remain fairly like this. Which is where now what you can do is you can reduce the load on the database by taking the data out of this database. This would help you save cost for the organization. So typically, building a multi-tiered storage is a way for organization to save cost by reducing the size, the amount of data that you are storing in the database. That's where the highlight is. That if I were to store, let's say 1 million orders in my database, out of which I'm only accessing 10,000 at this stage. Why the hell am I storing this much of data? Let me move it somewhere else. Now this database is small. The amount of data is small. The amount of data that I'm storing in a table is small, which means indexes are small, which means indexes can fit in memory, which means my database is performing. Right? This is where tiered databases or tiered data store comes in. So there is a very common nomenclature around it, but it's not a hardbound like nomenclature. Hot, warm, and cold, it's related to temperatures, but people just exchange. People say warm store is nothing and hot and cold people refer, but you'll get the idea when I talk about it. So hot store is which is a main transactional database, right? For example, for your order system, the MySQL database, where when user places an order, the database where it goes in and creates that entry is a transactional store. That's where your user facing transactions are happening. So that maybe MySQL, maybe DynamoDB, whichever database you are picking, that is where your reads and writes happen, right? These databases are low latency databases. Like in MySQL, when you write into it, it's low latency database, right? It gives you very strong consistency, right? Because that's what you need when you are doing end user basic transactions. But they're expensive. You say, but MySQL is cheap, right? Caches are expensive. This is relatively expensive, right? When you're seeing at scale of Amazon, if I take example of that, the amount of data, the amount of transactions that they are handling is relatively more expensive. What do you do then? This is hot tier. This is your first tier of data, which we typically design. Then comes warm tier. So warm tier is typically a tier which is there for your read-only workloads. Now, these read-only workloads that you have, it means that once your data moves from hot tier to warm tier, after warm tier, no one would be doing any writes on this data. You assume that. Once your data is moved from hot to warm, it becomes read-only. It is non-transactional, which means no one can write to the database directly. Like your end user queries will not write to this database. It will always go to transactional. But this is there to support frequent read-only data. For example, you are more likely to read your last 6 months of orders, right? Beyond that, very unlikely. So last 6 months of orders can be put into warm storage when you are frequently reading that particular data. It can be little slower, not as fast as hot store, but it can be little slower, but it needs to be scalable enough. Right? That because now you would take data from a hot tier, move into a warm tier. So it needs to be distributed, it needs to be horizontal scalable. In your hot tier, you can have one database to handle that load. I'm just using that as an example. But in warm tier, because you are putting in a lot of data and you want to read them, it needs to be horizontally scalable. And then comes your cold tier. Cold tier is where you have very infrequent reads. Let's say once a year sort of reads. That you can dump it on S3. And once a year, if I get even very less reads on that or very slow reads on that, it's fine. Right? So cold store is also read only. You typically store it in a blob storage like S3, in that too in a glacial tier. No one gives a damn about it. It's there. Like it's just there for accounting, legal. When a customer files a lawsuit against your organization, then you say, "Arey, now let's bring out that data," right? All of that. So you are very unlikely to access that data, which is what you put into cold tier, right? So this is multi-tiered storage that almost all big organizations have it. Almost. So whatever system you are building, try to see if you can archive something. I'll give very practical examples for that. Messaging apps. Now imagine Facebook Pay, you put in tons of messages to your friends back in 2008 to 2015, for example. How like do you even read them? Does it make sense for Facebook to store it in their hot storage and not even querying the data? What Facebook would have done? It would have taken the data, put it into a cold storage like S3. When you access it, then the first read would be very slow, but subsequent read then puts into this database and then you access it. But in most cases, it does not even allow you to access it, right? So why to waste your expensive storage on things that are not read or queried actively? This is the crux of it for which people build multi-tiered storages, right? Okay. So let me talk about a little bit more detail into practicalities of how the systems are built. This kind of architecture that I'm showing you. It looks overwhelming, but it is not. And this is what any data engineering pipeline looks like, right? So with this, I want to touch upon the key concepts of data engineering, where with technology fits in, and how data is moved and whatnot. I'll go a little more deeper into it, right? And again, a really practical way of doing it, right? Nothing's just like for the sake of it, right? So what we have is we have orders DB. We have order service. This is the main transactional database of orders, which is your hot tier, which is transactional. So MySQL, Postgres, DynamoDB, pick your favorite database where everything hot goes in. Now from this hot, whenever your order is new, the data is put into it. Orders, payments, logistics, what's not, they all query this particular database to get their answers. Once your order is delivered, which is where you have a job that takes what you want. You want this data to taken from your hot tier and move to warm tier, right? Because you are not likely to access order after 6 months, for example. So after 6 months, you may want to take your orders and move it to warm tier, right? So which is where you need a data deletion policy. Basically a job that says my data is 6 months old. So let me copy the data into here and delete from hot tier. All encompass into data deletion policy. And for every table, the data deletion policy might be something different. Let's say for Snapchat messages, it could be as small as 2 days because the messages are disappearing. So it's gone. 2 days pay, you can delete the data. Amazon order 6 months. For something, it would be 1 month. Right? So depending on use case, for how long you want to keep the data in your hot storage. And then what you want to do is you want to take the data from your hot storage and move to warm storage. Now, the property of warm storage is that it is read-only. It supports read-only workloads, right? Because here writes cannot go. From your end user, the writes would not go into your warm storage at all. It is only meant for read-only use cases, right? But the way you would be doing it, the way you would be structuring this information would be that it would be very efficient for you to serve the orders. I'll give a small example. Once your order is placed, the payment is collected, the logistics is sorted out. Now what you need, for you given an order ID, you want to fetch all the information from it, right? So when you're doing that, from an order ID, you want to get all the information about the order. You just don't need order information. You need payment, logistics, and everything in one response, right? So what you'd want is, you are not just storing your order details, but along with that payment, payment, logistics, and everything in one gigantic JSON document and keeping it handy in your warm storage. So what you do is, in your warm storage, you want to take data from multiple sources, aggregate them, and store it. So which is where from order service, you get data and you store it into a staging storage. It's just a staging storage. Typically it's S3 or any blob storage. So periodically you take data from hot storage, put it into staging storage, right? So in this staging storage, you get data from your order service. Then similarly from payment service, you get data into the same staging storage. From logistics service, you get data into the same staging storage. Data from all these three services, they come to the staging storage, right? Now what you do, you merge them, because what you want in the end JSON that you are sending, you want to send for a given order, the logistics information, the payment information, the order details, everything, not just order details. You want to send everything. So you want everything to be part of the same document that you are storing over here. So that, because this is anyway costly, you don't have to make multiple calls over here. So given we have to merge the data, payments, logistics, orders linked to a particular order, you dump all that data into staging storage using a dumper. So dumper is just a name that I given, which periodically reads the data and puts it into staging storage. But now here, assume there are 3 files, one for orders, one for payments, one for logistics. Now you will write a simple Spark job that would go through these 3 files, join them by order ID, and put them into warm storage. This is where data pipeline framework like Spark comes in. Spark does fabulous job into loading the data over here, transforming it, and putting it over here. Classic ETL definition. So here you have data from orders, payments, and logistics, which is read by Spark. The data is joined or aggregated and pushed into this warm storage. Right? Once your data enters the warm storage, your order service can now, if it's old data, it can read from warm storage. If it's new data, it can go to transactional storage, your hot storage. Right? So this is what your dumper with dumps to staging area goes in. From staging area, your loader loads it, which is typically your Spark job, and it writes to the warm storage. Right? Now, warm storage, the data is structured such that given an order ID, I'll give you all the information in one shot. You don't have to query separate data, separate payments, logistics and whatnot. Everything is there because this information is our read only. Once order is delivered, will logistics change? No. Once payment is made, would payment be changed? No. Once order is read frequently, now it's going to be little infrequent. Would it make any difference? Because it's literally read only. So what you are doing is you are just structuring the data such that it becomes very efficient for you to just make one API call to this warm tier, get the data, serve it to the user. Right? Okay. Now the question is, how would this order service know if I want to go to hot tier or cold tier or warm tier? How would it know? Right? Because all you have is an order ID. Given that you only have order ID with you, how would you know if that order is hot or warm? Because either data is over here or data is over here, right? For every request you make 2 calls, very expensive, right? So you need a way that given an order ID, if it's warm or if it is new or not. This is where your ID generation logic comes in. Remember, in ID generation, Snowflake ID, if you are talking about, the first 23 bits were epoch milliseconds. That is time. You can use that because if you know your deletion policy, you would know that, hey, it has been this long. So then where should I make my query to? Either warm storage or hot storage. It is possible that data might not be in warm, then you do a fallback on hot storage. Or if you're making a call on hot storage, then you do a fallback on warm storage. But that first 23 bits of your IDs, which is why having timestamp in your ID generation logic is very important. It just optimizes its entire flow. Right? Otherwise, you may want to have another database to store, okay, when was this order placed and all, then this needs to scale up. No. Store timestamp in your ID, which is why ID generation is so important, right? Having that time information in your ID is pure gold for use cases like this, because that would clearly tell you if what are the chances of my data to be there in warm tier and hot tier. Right? Okay. So this is how your data moves from orders to hot tier to warm tier. Now, similarly, what we do from warm tier, I want to move data to cold tier. Cold tier is S3, highly unlikely data would be accessed, very large latency. People don't really query them, right? So this is where your cold tier is. It's typical for accounting, legal, compliance stuff. So what you do, similarly, what you have dumper, staging, and loader, you do something very similar and put data onto S3. Now, when your data goes into S3, it's very unlikely that you would be directly querying the data. But in case you want to do it, you can use PrestoDB to do it. Now, these are all tools that are part of data engineering ecosystem that are very widely popular. So they might seem jargon to you, but just do Google search and play around with these tools, because 60% of infrastructure cost comes from data analytics. So you should know a bit of data analytics, like how these tools perform, how big data analytics tools work, right? So when you're storing data on S3, now either Now let's say if I define that after 6 months, my data should go into cold tier, right? So after 6 months, my data is in S3. But now let's say I want to query the data. How would I query the data? For us to query the data, can I directly make a call to S3 and read the actual pointed data? S3 is blob storage. We studied word dictionary. In word dictionary, we were able to fire queries on S3, pointed reads on S3. So for example, the way we define the data format in which we are storing the data on S3, it may open up things for us to directly read the pointed records from S3, which is where we covered word dictionary last week, where we defined that somehow like it is possible for us to make pointed reads on S3. We just need basic indexing file, basic data file, and we can still do that. And that's not the only format. You can define your own custom format, which is where your Apache Hudi comes in. I'll just write that note. Apache Hudi. Apache Hudi is the format in which data engineering teams write data on S3, giving them an ability to query directly from S3, which is where people typically use PrestoDB or AWS Athena, you might have heard of those things to directly query the data from S3. Right? So if you are making infrequent one-off reads from S3, you can do that. Let's say I just want a one-off information. It's not frequent. It's just one of that. Hey, I just need one information. It's not there in warm storage. It's not there in hot storage. It is there in cold storage. I just need one of information. One of queries, you can still query like this. Right? But there are cases. There are cases where you have to fire a lot of queries on your cold data. For example, let's say there is a police complaint file against your organization. Right? Let's say some case happened 1 year back. Now your data is in cold tier and police is asking you a bunch of questions. Now, how do you fire those queries? On S3, if you make pointed queries, it would be very slow, right? Plus very expensive because S3 has its own cost. Your infrastructure running PrestoDB has its own cost. So which is when you know that you are firing a lot of frequent queries on cold data, what you do, you load the data into a temporary database, which is queryable. Let's say there was a criminal who, or rather there was a person who is accused, not a criminal. There was a person who was accused of a crime. You know that person's ID. You are downloading all the historical records of that person. It's there on S3. You load it into a temporary database and later internal teams, your legal analytics and all, just query on it because you are making a lot of bulk queries for that historical data. So instead of making direct queries to S3, it is better if you load it, put it into a temporary database and then query it. So which is why you need a small loader that loads this data and puts it into a temporary storage. Once this job is done, you can delete this data. The data is still residing on S3. That's not a problem. You are just loading it into a temporary database so that internal teams for legal purposes and all can query it. And this is the most basic data. And this is where like almost encompasses everything around data engineering. The way you are taking data out, putting into staging, reading from that and putting it into multiple tiers is what data engineering team does. This is where your Spark comes in. This is where your PrestoDB comes in. This is where your Hudi comes in. So now if you are not accustomed to data engineering as a domain, I would highly recommend take a week, like take 1 or 2 weeks of your time and just explore data engineering stuff. There are so many amazing tools, libraries, frameworks, concepts that you would be finding. It's fascinating world out there, right? So, but this is what you would find almost everywhere. So what I did through this thing, we spoke about the implementation details on how those things are covered, how those data are moved, where components of data engineering like Spark, Apache Hudi, you would come across these terms. So where it would come in, Spark over here, Apache Hudi is the format in which it's stored. A lot of people don't like, unfortunately, when you look at the documentation of these tools, you don't understand where can I use it, which is why I'm just making it a little simpler while also covering how the systems are built, right? So this is where you'll find Apache Hudi. This is what would Spark would do, load it. PrestoDB, you would find it over here, which is actively querying on your quote unquote data lake. This is kind of your data lake written in Apache Hudi format, right? dump and load through staging, putting it on S3, deletion policies and whatnot, right? Just one caveat. From your hot storage, how would data be moved over here? This is where your CDCs come in, right? So from your hot storage, you're constantly taking data or using CDC and putting it there. So Airbyte, Airflow, those two, Airbyte and DBZM comes in, reading from CDC, putting it out. So what I would recommend is and it's big domain, very massive domain. So you need at least 2 weeks of time to just understand what's happening in it. But this would give you a very nice idea on how, and this is how most, like almost 99.99% data engineering thing is just encompassed over here. This is what you need typically when you are writing any, like if you ask any data engineering, this is typically what they would expect, right? And now it's your responsibility to pick one component and go really deep into it, how to use it, where to use it, write Spark jobs, write Presto queries, see what Hive is, see what Hoodie is, see what Flink, Flume, whatnot. There's tons of them, right? But this is how you design cost efficient not really Amazon, but cost efficient order system, where you clearly see a dip on the axis of your cost, which is where you have your hot tier, warm tier, and cold tier, right? Okay, before we move forward, any questions on this? Yeah, Rajiv.
With payments and logistics data, which we are putting into dumper for later merging, payments and logistics. So do they go in the hot DB or they have their own hot DB?
No, they have their own, right? Basic payments have their own database, logistics have their own database, right?
So they also have the same problem, right? You need to move the data from hot to warm to
exactly
cold.
Same. So same dumper, like you will have different pipelines to read from that database and put it into staging storage. From there, you merge it and you put it into warm storage.
By pipelines, you mean
Spark jobs.
Spark jobs, okay. So they pull the data, they have the policies over there.
Correct.
And also policies, like policy could change, right? I mean, let's say policy change, dynamic, you have some metrics and you figure out, okay, 6 months is still very, I mean, not Amazon, but you are in an early stage and you see 6 months is a lot much, we could go to 3 months. So that means you also need to make a cache, right? So that if any change comes up in the, I mean, policy cache, you have a policy ID over there, such that if any change comes into the policy, the services should actively fetch the new policy and then look up, do some processing based on that. That's
implementation specific. Yeah. So if you are that frequently changing policy, because changing policy is not so frequent, right? So you can do a redeployment in that case to take your new policy in effect.
Okay.
Right?
Okay.
Because it's not live, right? It would happen once a year or something. Right? You would not change it that frequently. Right? You can just do a redeployment of your stuff at that.
So can I take it in a general formula that whenever a config change happens infrequently, basically, you do a restart of the box, redeployment?
Yeah. Always. Don't over-engineer. Because if something is changing, let's say once a month, why would you want to take care of doing it in quote-unquote real time? No need.
Okay.
Sure. Thanks for that. Aman, go on.
So I have a very quick query.
Too low. Now it's better. Go on.
So I have a very quick query. Like, can we consider staging storage as a cold tier?
Staging storage as cold tier. Yeah, you can consider that. So long as you are able to query on the data. There is no, again, there is no hard and fast rule. This is how it should be. You can also use this staging storage as this and like directly write Hoodie files over here if you are okay doing that. You can do that, and then it's your job. So, which is what I said, there is no hard and fast rule to anything in tech. It's all up to you, your implementation. Right? But yeah, you can do that. Sure. Harsh?
Yeah, so that one point is not clear to me, that in the very last bottom, that, what is this temporary storage? So, for example, if query is coming to historical data, So
for example, as I gave you an example of, let's say, there's a police complaint file against a person. You are not making one-off queries to S3. You are making a lot of bulk queries. Now you are investigating that, right? So what you do, you would download all the records of that user from S3 and put it into a database. So that, because firing a lot of queries directly to S3 is very costly. Very costly.
Okay.
Right? So what you would want to do is you want to just dump all the data for that user, load it into a temporary database, and then query on that directly.
And
So
then
that
we
you
enable.
save the cost of making pointed queries on S3.
Okay, yeah, it's clear now. Thanks.
Yeah. Shreya?
Yes, yeah. So I am a bit confused about why do we really need the staging storage? As in, payments data would be also related to some other table. So, like,
So
why are
all
we
of those
really
would come over here.
combining?
All of those would come over here, staging storage.
So then, what is OLAP exactly? Like, it's used for analytical
OLAP,
things.
use a specific example. Are you talking about BigQuery/Redshift or a data warehouse?
Yeah, I mean, anything used for analytical. There, do we like store it just combining everything?
Yeah,
I
but
mean,
that is
isn't it?
queryable. S3 is not queryable, correct? What you're
Hmm.
talking about, OLAP, BigQuery, Redshift, that's this, correct? Where you are actively allowed to query the data in a relatively faster manner, correct?
Yeah.
Right? Will you be able to query with that frequency on S3? No, S3 does not support that because it's not meant to serve that use case. So this is what your BigQuery Redshift is all about. You're still doing a
Okay.
lot of reads on that, which are costly, which is cheaper than your transactional, but all the data from all the places come into this your data warehouse, which is your OLAP, and then you're querying on it. Whoever wants to query on it can actually query on it.
So do we
Got it?
have to keep it joined?
It's up to you. In most cases, yes. In most cases, you have to pre-join the data and store it because otherwise your queries on this, if you're doing the same kind of joins over here, that would make this very expensive. You would require massive compute to do that. So you typically do pre-join, pre-aggregation of data and store it in a very consumable format.
Okay.
So it's all depends, right? Basically, again, as I say, there is no hard and fast rule over here. Whatever keeps your cost down, you do that. Whatever fits your use case, you do that.
Okay. Yeah. Thank
Hemant?
you.
Yeah.
Hemant?
I have two questions, Arpit.
Hmm.
First, maybe on the cron side.
Hmm.
So as soon as we, let's say, pass the 6 month
Hmm.
of our work,
Hmm.
we will see that orders are there always. And for one of the user or another user, the
Hmm.
time is passed. And every second you have to remove something.
Hmm.
Is there other way other than cron where we can achieve this thing in a bit more efficient way?
No, so cron implies anything which is repetitive. It does not mean a simple cron job. So you can also do this, that once your data is taken out by this dumper and is loaded into warm storage, this loader deletes the data from hot tier. This cron only signifies that there is something repetitive which is happening, which is pulling data over here. As simple as that. It does not mean that your data is automatically getting deleted from hot tier, because you need to guarantee that your data is there in the warm tier before you delete it from hot tier. Correct? So what you can also do is you can let your loader delete the data from hot tier.
Yeah, I'm thinking a load on a DB that all the time
load on the DB. You
Yeah.
can do it once a day. Like you can batch the deletion and run it once a day on during off-peak hours.
Okay, so I mean the best strategy looks like in place of doing this thing continuously and putting a load on a hot, you can take like on a day and or whatever time, you try to get all the data which are 6 months old or something and
And then you
remove
delete it. Yes.
It's bad job, looks good,
It's
better,
bad job. Yeah.
but maybe
Yeah.
maybe not cron. Okay,
Yeah.
that's
Yeah.
the one
So
thing.
when I say cron, it's more about having some process that is doing it
Yeah.
for you.
Okay, got it.
Yeah.
Maybe then second question is towards this order data. We need it from two purpose now in future. One is
Mm.
the transactional form where we want to know, okay, for this user's data around 7 months ago or something, where you know the order and you need the order ID, and then based on that you fetch it. Another is for all the analytical purpose, we need, let's say, want to know our analytics team wants to know the all orders of from users which has greater value than X. Okay. On those cases, we need that columnar form of the data where you do not try to store on row base, but in a columnar format, because those queries are suited.
Correct.
That kind of. So in this picture, where I should kind of plug the analytical DB, what I'm thinking, plugging with here in the worm, what you have mentioned, looks not so good. I'm not why I'm not feeling comfortable on this is the purpose of analytics is always you as soon as you get the data, okay, it is in hot, okay, and you also need to do analytics on hot also. Warm reads based on whatever your cron or batch job is. Those data come.
So
But
if that is your use case, then your writes can directly go to your analytics DB. You don't have to wait for the dumper to kick in only 6 months old data. Now what you are doing is you are adding a new constraint. You are adding a new requirement that you want to do deep analytics on a real-time data, and which is where I have not drawn that because it's not part of our specification. Now what you are specifying at this moment is my hot data. I'm not able to do analytics on my hot data. Correct? Now what you can do is your orders, when it writes to hot data, you have another thing which is dumping it into, let's say, your Amazon Redshift and whatnot, like this, right there and then. Kafka, Kinesis, pick your favorite tool, CDCs and whatnot, right? Okay. All the data goes into this hot tier analytics where you are doing, which is kind of your Amazon Redshift, Google BigQuery, right? If you want real-time analytics, then you build that pipeline that in real time flushes that. It does not wait for 6 months time period. What I was describing was that 6 months duration wala pura flow, right? If you want to do that unified analytics on that also includes your hot data, then you have to immediately push the data onto this side, onto your data warehouse, like Amazon Redshift and basically Amazon Redshift and BigQuery.
Okay, so got it. I mean, the solution is to use a separate path from order service, from order service to put it in a OLAP.
Yeah.
And maybe just a follow up on that. From the perspective of load or scalability, what should be the pattern? Should I put it in a async way, like, because it's not immediately needed?
Okay, data in a async way.
Yeah. The order which are coming, okay, writing in a transactional DB is a sync job, I will say.
Correct. Yeah,
it is sync. Do it in sync. But orders writing on a OLAP is a kind of async. Okay. So is it advisable that from orders it goes to let's say a Kafka, and from there we write in a batch, because writing on a OLAP is a costly affair.
Correct. CDCs come in handy for that, right?
Okay, so that's why one question is CDC. We should use CDC or
we should use CDC, which is plugged onto this database and takes the data, transforms it, and puts it wherever you want. Because CDCs would kick in immediately, right? Whenever there are changes, it is constantly reading from the database at that moment, right? So you can use CDCs for that. Don't plug it in from here to Kafka and all. Whenever it's about data, you directly plug CDCs and read it and then store it wherever you want. So even this can be a CDC.
Yeah, actually, my thought started from that. Can it be CDC? Then I thought,
wherever it's data. You're reading from the database, wherein you're dealing only with data, because it does not require application context at all, right?
Yes.
So you directly read from CDC rather than relying on some Kafka event coming in from your API side, because not everything would have a Kafka event, right? That is where CDC comes in, and you read and you put it wherever you want.
So CDC can have two different destinations. We can like once CDC receives the data, it can go and write in two different, one on the dumper side for this and another for analytics side, because both are different. But that solves the purpose with very clean architecture.
Yes.
You have a CDC running on the hot, and it serves both of your cold, warm storage and also the analytics part. Okay, thank you. Thanks
and this is where CDC shines, right? Yeah. Which is where you should not rely on API server to push it, because you are dealing with raw data. You want data to be there, no matter what table you add, no matter what kind of updates you make. You are not expecting to have Kafka events for everything. So CDC is the best place from which you can pull the data out from the database and do whatever you want to do with it.
Yeah. I got this idea yesterday when I was reading a DB log from Netflix. They created a CDC, not open source as of now. In 19, a paper came out. They're trying to do the same thing because they have all these kind of things. Okay.
Super. Thanks for that. Sure. I'll take one more question. Go on, Mohan.
Yeah. So from the relational databases, typically, right? So the transactional databases, we are creating the margin. Is there any loss of information if we want to reconstruct the original picture?
No. Why do you think there would be a loss? I'll address that.
No, because we are creating like a from relational store, right? We are flattening out the structure most
Yes.
likely because we want to input JSONs and things like that, right? So obviously, when you are flattening out the structure, so there might be a case where kind of maybe, I was just wondering if do you kind of capture each and every attribute of in those data stores?
Literally every single column of every single table of this database is stored in the staging area. Literally everything. And from there it is merged. So what happens is literally imagine n tables having m columns, all of them as is stored on this S3, being read by loader, merged on real time. And this is where that JSON object is created in the memory of this loader and written over here. So you would not have any loss of data at all. That entire table with that entire structure is stored over here.
Okay.
So in case you want to construct this, you can do that. So there would not be any loss of information. And you should not design it such that there is a loss of information anyway. So here you literally have every single column copied.
Okay. And second thing, is there any flattening out in the sense that, for example, orders and items, right? So if you imagine if you flatten out in an Excel, right, the same order ID will be repeated across, right? Something like that. So does something like that happen, or because of JSON, it is efficient structure?
Typically with JSON, you don't need it. But in case you want to flatten it out still, you can do it over here. For example, you have a table, like rather here also, I'm just drawing it like one S3. Here also you have multiple stages of data. Like you have your raw data, then you have processed data, then you have semi-processed data, then you have optimized data and whatnot. Right? It goes deeper into this. It's literally how you form data lakes. But the idea is that have a place where you are dumping your tables and all data as is on one place on S3. Then if you'd want to flatten it out, if you'd want to make it denormalized, you can do it. Right? So there is no, but have one place where your actual raw data is stored. From read that and create a flattened data. That flattened data you can read and create JSON out of.
So whatever you're proposing in WARM is typically a structure like that, or it based on it's
no, in WARM I'm proposing to store everything that you need to be served to your end user, which is queryable as is. Like given an order, I want all the information for that order in one JSON. So it's literally structured for me to just like directly send to the end user.
Okay, understood. So I might want to then add additional formats.
Correct.
Based
over
on
here.
the use
Yes.
case. Okay.
Yes.
All
yes.
right.
Yes.
Thank
But you see how this architecture makes it pluggable, where you can just, if you want different types of use cases, you just have to change the staging, write pipelines that run just writes back to the staging from which you can consume and fork other things out. Right? That solve that other use case well. Okay? But the overall flow would still remain the same.
Understood. Right? Thank you.
Got it. Sure. Oof, great discussion. Okay, now addressing, before we start designing S3, I think we'll take break before we even start designing S3. I was thinking that this would wrap in 30 minutes, it did not. So we'll take break in 5 minutes. But before we brainstorm on S3, which should be a massive discussion. Before we brainstorm on S3, I just want to leave you all with thoughts on things that we discussed last week, because they will all be coming in handy when we design S3. So last week we built word dictionary on S3. Word dictionary that we designed, that one format with index and data, is kind of like an embedded database. We stored on S3, which was dirt cheap, but it had very costly access. It can be used as cold storage with infrequent access. We just designed an order system leveraging that. Right? So when a tool, remember this, whenever a tool says we give you an ability to query directly on S3, like AWS Athena. Athena gives you this tool. Presto gives you those abilities. Hive queries, you write Hive queries to do that. Behind the scene is powered by Spark. All of that, their way your data is structured on S3 has to be such that it has that information to make that pointed query somehow. Right? The big data engineering tools like Apache Hudi format or Spark SQL and whatnot won't go into those details, but all of that create data. When they write on S3, they create it such that they have that meta information. And then so that they can make pointed queries on it. Right? Okay. Another thing that we studied last week is Bitcask. In Bitcask, we saw how log structured storages are important, how they give you performance. And we understood where it comes in handy. It gives you very good performance on cheap commodity hardware, like magnetic disk storage, right? Kafka or any similar tool that you pick, whichever they say that they are high throughput system, behind the scenes are powered by log structured storage. So if you go to Kafka internals, when Kafka accepts the write, the message that is there is literally written in one append only file. There is no magic behind it. It reads it and it writes in append only file. It reads another write gets, it writes in append only file. So for every single partition in a particular topic in Kafka, simply assume this, like oversimplification, but you'll get an idea. Every topic has n partitions. Each partition is one file on the disk. When a read or when a write comes in, it knows it is for this topic, for this partition, it goes to the corresponding file and appends it at the end of it. When reader reads it, it knows that from this file, I want to read from this offset. The byte offset of this is maintained in Kafka that, hey, this is the consumer, which was reading from this partition and has read till this offset. So you can literally build a micro version of Kafka in a matter of one day using log structured files, simple append only files. And I would highly encourage you to do that. Like, this is how I built my understanding of Kafka really well and the internals of it before I started diving into the source code, because this is what it's all about. So what I would recommend is take this as an exercise, code it out. For every, like, just create one topic, n partitions, create n files, open all of them in append only mode. When you get the write, pick one file, write the data there. Write a reader that is reading from these files step by step, because in Kafka, you read sequentially one after another from a partition. This is where you're doing something very similar. Don't think of making it distributed. Don't go into those complexities, but at least build a small prototype. You'll get very good idea on how Kafka works internally, right? When you build it, you get that joy, right? Okay. Then where you use log structured storage, now because it gives you very high throughput on commodity cheap hardware. So think of log structured storage wherever you are getting very high ingestion rate, really high ingestion rate, and you are doing write heavy workloads, not read heavy, write heavy workloads. When your system is having write heavy workloads, you want to accept a lot of writes coming into your system and you want to write it as fast as possible, which is where log structured storage shines. Few examples: metrics, analytics, clickstream data, any system. You pick New Relic, you pick Datadog, you pick Google Analytics. All of them are backed by log structured storages. Not as the primary storage, but the place which accepts it. Most of them, they say that we write to Kafka. Kafka itself is log structured storage because it can support very high write throughput, right? So this is the magic sauce behind any system that claims to be a high write throughput system. It's always backed by a log structured storage. Kafka is an example for that. So when you say I'll use Kafka over here, you're effectively using a log structured storage, which gives you an ability to write on a cheap commodity hardware at a very high performance, which is why Bitcask is so important, right? Okay. This is what a glimpse of the previous thing is. All of this will come in handy when we design it. That's why I just gave you a refresher for that. Okay. So now what we do, we take a break because now we have to get up for a very huge discussion for 1.5 hours or almost 2 hours. We'll talk about S3, right? We'll talk about S3. We'll design S3. I'll let you all folks have some downtime. We'll sync back in at 10:05, 6 minutes from now. At 10:05, we'll resume a very deep brainstorming on S3 and very interesting points to cover. First of all, this is where you'll see why consistent hashing is not the magical solution. Consistent hashing fails while scaling S3. No one uses consistent hashing. We'll talk about it why, right? Then we'll talk about storage, how to make elastic storage. Then we talk about handling hot partition problem and access and a lot of other granular details of it, right? Every single decision will be very realistic the way we talk about it like this, right? Okay. So we'll sync back at 10:05, 6 minutes from now, and then we design S3 with our brainstorm. Okay. Sure. See you folks in 6 minutes. Okay, let's start with designing S3. Big discussion. Okay, party. So S3 is a key value store. So yeah, so what happens on S3 is your key is the file path that you have defined. The value is the file content that you are storing on S3. So S3 is actually, and I'm not even making it simpler. It is actually just a key value store because the notion of directories on S3 is logical. Like on real world, when you create directories on your file system, it does not mean that on S3, when you're creating it, it is getting created that way. It is at that path in the file system. The concept of directories and folders on S3 is actually logical and virtual. For them, it's simple. This is the path. This is the file. That's it. Right? So S3 is a gigantic key value store where values can be massive files, terabytes big files. Right? So which is why you would have seen that throughout this course, we designed so many key value stores, because key value stores are actually the foundational building block for so many systems. Right? So S3 is just key value store where values can be gigantic files that needs to be stored on disks, right? So you cannot store it in memory. They are gigantic, which is 1 terabyte is also a common, length of file, right? First, so now which means that what we have to do is we have to think of the storage side of things. That hey, if we are just building a key value store, right? Always remember this, right? It's just a key value store that given this file path, I want to write this content. This is, let's say I just make it simple. I say that, hey, in an HTTP request, what I'm getting is, I'm getting that, hey, put this file, which is the content of the file, at this particular path, right? This request came to our API server, and now our API server needs to write it to storage. Obviously, you cannot use a transactional DB like MySQL to do it, because there is huge amount of data. You are writing GBs and TBs of data, right? So now let's talk about how do we design, or how do we define storage layer for S3. Now, the requirement side of things, the storage of S3 has to be elastic, which means it should grow when you need it, right? One key thing, when you write a file to S3, you always pre-tell S3 that this is the size of the file. You never say, oh, this is a stream of bytes and keep on appending to a file. You always say that the file that I'm writing has length of, let's say, 1 GB, and then you write into that file. You never do this, that you say, yeah, I'll just keep sending you bytes and keep appending to file, however big it can get. You never do that. You always pre-tell S3 that this is the size of the file that I'm writing, and now comes the bytes of that file, right? So now what you need to do is we need to design a storage layer for S3, which is elastic in nature, which can grow as we want it to grow, because S3 is an ocean of data. So how would you design the storage side, literal raw storage side of S3? The access is key value based. Directories are logical. They don't hold any significance there. And it needs to be like it needs to grow on its own. How would you go about it? Raise your hands, I'll pull you in. Apply first principle thinking. Don't think in a very complicated way. Keep it very simple. And typically the simpler you think, the better are the chances that that's how it would be implemented. Right? Rahul, go on.
So basically, one way I can think this as is, we will just provide a pointer as a value and allocate memory to that particular block of like 1 GB, basically.
But what's the pointer there? It's disk, right? Pointer disk.
Yeah, disk.
Yeah,
disk. Yeah, like some sort of like values like disk disk identification number and the address on it.
So saying that this is your disk. Let's say this is disk 1, right? On which you say, okay, please reserve 1 GB file for me. Let's say this is where it reserved. So it has some meta information. So some file path on the disk where you are storing this, and this file path can be separate from that other file path that you have. Okay, so some file path you have where you are storing this on the disk, maybe similar to that, some ID and YD and whatnot you added. You reserve this 1 GB space. Now,
like there is also one more thing that can be done is like I split these bytes into some partitions.
No need. Let's keep it simple. And S3 also does not chunk everything. Don't overcomplicate. Keep it simple. That is performance optimization. Now, first let's decide the basic part. Then we'll go into advanced stuff.
And also like S3 has some amount of copies of the data that we send.
That is different. That is performance. Let's just think of one pele. Let's solve one problem now. Those are additional features. Let's solve this one problem. How is your storage? Because now this disk would have some capacity. Let's say 100 terabyte disk. What happens when this fills out? We need to think of that, right? Storage. We are still not done with simple storage. Then we'll go into durability and other part. I have all of that covered, right? But let's first solve this problem.
So basically, so basically it would be like disk identification dash the address or something like that.
Okay. Let's say I have 1000 GB of storage. So now you stored this part. Now what happens when you get more writes? You would fill out on this disk. Now what?
Yeah. So that's why I said disk identification in the sense disk 1, and this is the address on which you need to read to get this file. And like and when this disk fills out, we will create another disk with the new identification and same thing. Pointers.
Okay, fine. Thanks for that. Let me pull in Hemant. Hemant, let's build on top of this. Now, what would happen? Let's go into those micro decisions when you're storing files on this disk.
Yeah. So maybe the first thing what Rahul says is we need a indexed which identify the disk and the location of that disk. Now, if we go and start understanding that we have to allocate disk space. We need to worry about how much we can allocate and how. If we say like I have 1000 GB and I'm looking for up to a 1 GB file, then I can have a pointers only for 1000 specific key value pairs, which seems like a overkill to me.
No, not every file will be 1 GB, right? It depends, right?
Yeah, it depends. But initially, when we are saying we need to have,
you cannot start with that assumption because people can write small files also.
Yeah, that's why the problem is we have to figure out a solution how we allocate a size for a given file.
Correct.
Okay. So there we may need to think about the chunking, as you said in between. That
no need. Keep it very simple. Think of it because chunking, you don't need chunking at all. To be honest, you don't need chunking at all. Now then here on this disk, let's start with this. What is your key design decision when you define this disk? What type of disk are you using and why?
Okay, it definitely whatever we have learned from previous systems, we are saying that these are the key value pairs where you are going to put it something for as a value, and the value, if it changes, we can kind of provide a separate pointer. So they should be kind of a write only, which can be a sequential. Like, okay, you start writing from start to a point, and then you do not need to modify. So we can use something which is a continuous storage, where you go once and append only. So whole 1000 GB disk starts from sector 1, block 1, and you start adding one by one each of the pointers. You started, finished. What
you are describing is a log structured file system.
Yeah. It is saying I started from 00 location of the. I reached to 10, then from 10 I will give another pointer, and let's say that goes to 35, then I will
got it.
That next is 35. So that's a log.
But why did you go for log structured file system? Okay, but basically before that, let me brief folks about it. Okay, but even before that, what kind of disk are you using? What kind of disk are you using?
Are you talking about SSD, HDD? Are
Yeah,
you saying?
yeah.
Yeah, definitely. Here, what it makes sense is like a disk where I can go and write once easily by seeking to a given location. So that is good, I think, for HDD also. Uh, what the problem with HDD is to seek a location and then write it. Where SSD size, because you do not need to do that. So
Correct.
here, I think HDD is good enough because the way we are designing the system.
But what other factor will you consider in picking HDDs and SSDs? Magnetic disk versus SSDs.
Read and write throughput of the system of that disk, that how big files are. So let's say I have support like a 1 GB file. If my file format system is not supporting, then it is not making sense. That plus what kind of a cost it gives on me.
Cost.
On
Everything else is secondary.
Yeah.
Because imagine on S3, the amount of data that we are storing on S3 is so huge, so huge that if we store it on SSDs, that would shoot up the cost like anything. Right? And the amount of data, like it has multiple exabytes of data, which is insane. I think it's 7 or 8 exabytes of data at this moment. It's huge amount of data that S3 is storing at this moment. Given that, now what would happen is if you store that much of data on SSDs, again, this is like hot tier and cold tier, kind of that. If you're storing on an SSD, you get very fast reads, very fast writes, but your cost would shoot up. Now, which means that you would want to have a very nice margin where it becomes a profitable business. You need to go with a cheap commodity hardware. So which means the first thing that you fix when you're designing an S3 is that you need to go with magnetic disk storage. Now you start with that because that is cheap, and commodity hardware, you'll get better margins. Business comes first, engineering, everything second, performance. We'll try to get the max out of the constraints that we have. So we start with this constraint because we are building an ocean of data. We start with HDD. Now, as soon as we start with HDD, now starts to kick in the point, Hemant, you said about performance, that HDDs are not performant in doing random writes. So Jyotinder, what would we do? If random writes, we cannot do random writes because HDDs are bad at it because of magnetic disk movement. What's the solution to that? To get similar performance as SSDs?
Like we just do append only writes.
Right? So that's where we want to do append only writes. But it's not like when we talk about append only, we typically talk about within a file append only. Here, the entire file system is append only. That whenever you write, it will always write to the next sector. It was never that your first write would go over here, then write over here, then over here, then over here, then over here. It would never be like this. The entire file system is log structured storage, which means that whenever you write, it would always write from the first sector to the nth sector and would fill out data like this, no matter what. So some caveat, the file systems that we typically use, FAT, NTFS, EXT, BTRFS, any, in your operating system, the file system that you have, they have the core responsibility of that file system is to figure out that when someone asks for a particular file path, where on the disk will I allocate that file? And it's the implementation of file system that dictates that this is where you need to store it, this is where you need to store it, this is where I can store it, and then defragmentation and whatnot, right? All of that comes in. So that is what your file system does it for you. So on a normal file system, the things that you have is that this is the file path. This is the inode. Inode is a very common concept which tells you that basically path is part of inode, but you'll get the idea that I'm just making it, I'm just simplifying it for everyone to understand. So let's say if I have a path /home /arpit /1.txt, right? If this is the path, on this path, I'll have an inode. Like, so my inode would store this information that where exactly on my disk is this file stored and how big is the file. So it would know that on this disk, this file is stored from this location to this location. So that information will be part of my inode, right? Now, this is what the key value that we're talking. We don't have to explicitly maintain this. your file system implicitly does it for us. On your file system, you define a path that at this path I'm writing it. Your file system itself. So when you browse through your local file system, your Mac, your Windows laptop, you open C drive, you double click on that folder. How does it know that these are the files within that? It needs to store that somewhere, which is where your file system comes in. Your file system stores that information in a directory, which is what is called as directory, in which there are multiple inodes, entries there. Inodes contain the meta information about the file, like updated at, created at, modified at, file size, file format, and other information like who created the file, who can access this file, all of that information. So when you run ls minus l, the output that you get is typically the meta information of the file that is stored in the inode. And the way it is getting that information is making a file system API call, getting that information and rendering it. This is what happens. Now, this is what the key value mapping that we're talking about is stored implicitly by the file system. We don't have to do anything that you just have to, in this file system, in this hard disk, just create this hard disk just use any log structured file system and you start writing file at a particular path. It would internally maintain this mapping for you. You don't have to do anything for that, right? But when you're doing it, because it is log structured, you need to tell them that, hey, this is the size of the file which I'm writing. This is the next file. This is the next file, whatever you're getting, right? And then it would start writing on those locations. But it will always move, as Hemant said, always move from sector 0, sector 1, sector 2, sector 3, sector 4, sector 5, so on and so forth in a sequential fashion, no matter what, right? This is a very important design decision that we are making. Again, we don't have to maintain this mapping. It is done by your file system implicitly. You just need to know which hard disk your file resides in. That's it. And then you make a call that give me file from this path, it would give it. Okay. Okay. So this is what you have at this moment. So now, Jodinder, my question to you is, what happens when this fills up? What would you do?
You need to start sending write requests to another disk or data node.
So another disk you are adding it. Okay. But now, how would you know, or rather, okay, let's say even this filled up. Now what? You add one more.
Yeah.
And then this filled up. You add one more. Correct?
Yes.
Now, this is a very common way to do it. But then what kind of, and now what you're doing is, where are you writing? So you need to have a way to know which is your current hard disk where you're writing. Correct?
Right.
That becomes, let's say that is nothing but a head pointer, kind of linked list. If you look carefully, this is actually being formed as a linked list, where we have a head pointer that tells you which is the active disk where you have to write, which is what we do. In S3 or in any blob storage, everyone knows that this actually, now let me go into a little bit more detail. Now this actually is nothing but a storage rack. The storage rack that you have, this is exactly what a storage rack looks like. A storage rack has a huge number of hard disks, which as in 100, 200, not that much. 100, 200 hard disks. They are attached, they are plugged into the storage rack. And when you are writing to that storage, you know that this is the active hard disk in the storage rack where I would write it. And it writes from there. Once a hard disk gets filled up, this pointer moves below. And now the other hard disk becomes an active hard disk. And this can be maintained by a proprietary storage rack software who maintains that this storage rack, and this is where hardware level changes, embedded system, not embedded system, but basically hardware level device driver changes comes in. So in most cases, storage racks comes with a device driver that maintains this pointer for you on this is the active hard disk at this moment. If your storage rack knows that this is going to be a gigantic log structured file system. Right? Now, going bit more might seem little abstract, but this is how it is. And just to give, if you want to know a bit more details about it, just go to Dell website. You'll find, so Dell has amazing set, Dell, verbatim. So Dell and Verbatim are market leaders, and even WD, like how can I forget WD? Dell, Verbatim, Western Digital, these are market leaders in storage space. They give you or they sell storage racks like this. So when Amazon, Google, and all of these companies, they build it, they choose to, like now they have started manufacturing it, but they typically get this cheap hardware from these companies and they put it there. Right? So now what happens is the storage racks, the device driver of the storage rack keeps this information. It's now pluggable over there. Right? That which is the active one, it starts to forward to that once a hard disk fills back up, and then it reshuffles and whatnot. So you can directly interface with this. You can directly interface with this storage rack driver and ask it to do whatever you want to do. So it abstracts out the complexities of this hard disk. Now, the storage rack that we are talking about, this storage rack having multiple hard disks, this is one of the configuration where your storage rack knows that the underlying hard disks that you have is log structured format, kind of connected in a linked list. It's all maintained by the storage rack itself. So it's typically masked out from the implementation detail. Like you don't really have to worry about it, but it takes care of that. But I'm going a bit more details on how it actually functions, right? So in I got one place. So during my BTech, I used to manage, and I was part of the managing team which used to manage data centers for my college. So somehow professor loved me, so he always used to invite me to data centers, which is where I first saw a storage rack kept in a very cool temperature, roughly 12 or 10 degree AC room, bunch of storage racks, where every internet request made from entire college used to go through that. It was the proxy. It used to go through that. It used to make request on the internet, get the response, store the web page on the storage rack and send it back. And so literally every single web page, every single student or teacher accessed in last 30 days were stored in this gigantic storage space. And we got to know about it. So we started all the funny activities that we used to do, because this is very risky, right? But whenever you are behind a proxy, remember, anyone can do anything with it. So you need to know which network you are part of, which is where I got exposure to this thing, like how the storage rack works, what kind of things it does, what kind of interfaces it provides. So one of the responsibility that I had at that time is if one of the storage rack gets filled, because it's just temporary data, I was allowed to delete that, which is why I got to know that how to interface with the storage rack and how to ask it to delete something if we want to. Here on S3, we don't delete anything, but I'm just giving you a glimpse that if you want to know deeper details of it, just go through Dell, Verbatim, Western Digital, pick your favorite, go through their product specification of storage racks. You'll find all of this information. Will be a bit more technical, but go through that. It's very fun exploring those parts, right? But here you see how beautifully this fits together as an purely elastic storage. Now, this is one storage rack that we are talking about. Writes are coming in from your users, going into the storage rack, right? One hard disk fills up, it moves to the next hard disk, it moves to the next hard disk, it moves to the next hard disk. Now I can add as many disks as I want. But storage rack has a limit, because storage rack is a physical hardware in which you are inserting the disks there, right? So because there are limited number of slots, let's say 20 or 30 slots, you cannot go beyond that. So which means that you would have multiple such storage racks. And then you would do one storage rack is done, I'll move to another, then that storage rack is done, I'll move to another, then another storage rack is done, I'll move to another, and so on and so forth. Right? So this is what you do. So I simplified it by explaining one storage rack, but you would have multiple such storage rack in your data center storing all of this information. Okay. Now, how big one hard disk would be? Let's start with that. Jyotir will continue with that, and then I'll pull in Anupam. How big one hard disk would be?
Like it depends, right? It can be as big as possible. It can be 100.
Guess a number. Guess a number.
100 terabytes.
100 terabytes.
Yeah.
100 terabytes hard disk is very costly, right? So
Yeah.
you chop it down, right? 10 to
Right.
20, each hard disk is 10 to 20 terabyte big. And in one storage rack, you would have 20 to 30 nodes like this.
Right.
Right. So the amount of data that one storage rack can handle is 200 to 600 terabytes. Huge enough space. Right. This is what 1 terabyte would this is what one storage rack would handle. Right. Okay. Now, one small caveat over here. We think, oh, it's just 600 terabytes. It's not huge. A lot of us would think that because we are so accustomed to hearing 1 TB, 100 GB, 200 GB, like it's nothing. But for a business workload, for a corporate workload, for any mid-sized organization, even big companies, the kind of things that we are storing on S3 is always some kind of text data, either dump of our database, either some files that we are temporarily creating, right? Some processing that we did. In most cases, it is textual data that we are storing, typically dumps of our databases in most cases. Apart from that, we also use it to store media objects, right? But in most cases, you would see that 100 terabyte is a huge space for almost any and every organization. There are very few who go beyond that. For most people, for most organizations out there, this is big enough storage space for their lifetime. Right? Don't go into extreme. Extremes are like you cannot design a system considering anomalies are normal behavior. Right? You have to design systems for your normal customers. Extreme customers separate, like handle them separate. Right? So for your regular customer, this 600 terabytes of storage space is good enough, right? But what else do you need? So what you can do as a bare minimum, naive solution, give one storage rack to every customer that you have. Right? So let's say I have company ABC, give them one entire storage rack. Hey, this is your storage rack, do whatever you want to do with it. And you can just abstract, like this is how you allocate your resources in S3 for them. No matter how many buckets they create, no matter how many files they create, it's their storage rack, whatever they would want to store. So this way you get isolation of the load across your customers. But is that efficient enough? No, because what if when you assign a storage rack to a company, they just store 1 GB of data and then they never do anything. You are wasting so much of space. So which is why it is not a good utilization of your underlying hardware. So now we have to make it better. So now let's talk about how do you make your hardware utilization better. So up until now, what we discussed is we discussed around whenever write request comes in, we store it in series of hard disks connected kind of like linked list, abstracted by the storage, basically abstracted by the device driver of the storage rack, which keeps track of, this is the head of my storage rack, which is I'm writing. You can also choose to implement it on your API side if you want to, where you are keeping track, okay, this is the head of the storage rack. Either way, it's possible. And when one disk fills up, you add to another one and then to another one, then to another one. Right? And everything is stored in a log structured format. Right? Okay. Now my next question is, given this is the structure, right? Now, how would you know, I'll pull in Anubhav. Anubhav, how would you know that a disk is full? And now you have to go to the next one. Someone has to tell you, right? Now the disk is full, go to the next one. Who would do that?
I think the file system driver, or not the file system. Yeah, the file system driver would have to do it.
So the file system driver is limited to this, right?
Oh,
maybe storage rack. Right?
Rack is full, okay.
Right? Racks one, right? Because file system driver is limited to one hard disk, right?
Yeah.
So The storage rack driver can do it. If that does not give you, so then what you do, you add your own small component whose job is to monitor it. So you add a monitor who is monitoring this and switching the head if you want to, right? So you may want to have now, when would you switch it from one to another? What do you mean when you say it is filled? Let's say I have hard disk of 100 of 1000 GB. When do I say move to the next one? When I fill entire 1000 GB, then I say
No, I don't think so. In that case, like we would be impacting throughput for writes because it gets filled and then some of the writes would be in pending state. So we should do it a bit before
correct.
1 GB.
Brilliant point, right? Because now what would happen? The way you put it was very nice. That now imagine, now this is where you would say, hey, let's start with simple. When I complete my 1000 GB, then I start writing to the next one. Now, when you do this, let's say just completed 1000 GB. And now what you are doing is you are changing the head. Now the write should come over here. So while this is happening, you cannot accept any other writes into the system because there is no space to fill over here. Now this is yet to take effect. So this is not a good idea. So which is where what you do is you define a threshold, typically 70%. That when your hard disk is filled 70%, you move to the next one. Right? You change the head, you move to the next one. So you give yourself enough headroom to complete the existing writes that are coming in, while the other hard disk is becoming the new head of the linked list. You are still accepting the writes happening over here. Once this entire write is done, then the newer set of writes can come to the second hard disk. This way, you are not impacting your any existing writes. And that is really important for when you are building a system that is 6 nines or 7 9 availability they give, 99.99999, 7 9 availability they provide, right? And you're giving that much of availability, you need to ensure no matter what, how many writes that are coming in, you are able to serve them. So you cannot wait until the last moment for you to do it, for you to push, or you want to start writing to the next hard disk. You would always need to do that when it's 70%, I'll start writing to it. So any existing writes that are happening can still happen. You have enough room available for you to complete existing writes. And then the newer writes can anyway start happening over here. Right? So this way you do it. Okay. Now on S3, you can also delete a file. Right? So when you delete a file, you have to remove the entry and then do a cleanup. So this is a classic case of merge and compaction. So now what we do is, because this hard disk are just 70% filled and there would be some entries that would be deleted, like that does not hold any stance at all. What we can do is we can merge the hard disk, and these are terabytes of data I'm talking about, right? Literally terabytes of data. You are merging this hard disk, removing the stale entries, or rather skipping the stale entries, removing the deleted files and whatnot. And you are merging them into a set of hard disks. So you are basically freeing up the space, doing defragmentation and making them re-available for reconsumption. This is why merge and compaction becomes important for you to ensure an efficient utilization of the system. Now, it was easier for me to say, I will do merge and compaction. Now, imagine writing code for it, right? You have to literally start iterating from one hard disk, which is why order n complexity is really essential when you're doing this, right? You will have to check for every file that you have, which is stored in this hard disk, see if that file is active or not. If it is active, you keep it. If it is not, you skip it. And then you copy those things into other file or into other hard disk. Now, this is where one more interesting thing crops up. Is around, what if I update a file? Now what happens over here? Let me pull in Siddesh. Siddesh, what happens when you update a file on S3?
I mean, I don't know what happens, but I can say what I'll do. Yeah.
Think.
I would write a completely new file.
Log structured file system, right?
Yes.
It would always write to the new sector, which means that when you are updating when you are updating an existing file, you are always giving S3 the complete new file object, correct? You always you give the entire file to be written on S3. Even though it is same path, it would go to a new consecutive location in the hard disk. So no matter how many times you update a file, you are always getting, you are always writing to new locations on the disk. Otherwise, you would do random writes and your performance would degrade. So which is why you are always doing sequential writes. So even if you write to the same file again, it would go to the newer location on the disk, which is how S3 is able to do object versioning. See how beautiful the system is. As a side effect of having log structured file system, when you're writing to new location every time, you are not deleting the old version. You can change, you can go and access the historical version of the file. This is what, when S3 says we give you object versioning, this is how they are implementing that, because their file system itself is log structured. So let's say, just a detailed example of that. Let's say I wrote my file a.txt over here. Then at the same path, I'm writing the file. And now this time it is written over here because it is log structured file system. It's append only. And now I wrote it the third time. So I have 3 versions of my same file, in which first I have wrote hello world, then hello world 1, and then hello world 2. I have 3 versions of my file. But because they are stored separately, because every time you are writing, it is writing to the newer location on the disk, and across the disk, you can actually go back and access historical version of the file, which gives you object versioning out of the box. So when you enable object versioning on S3, it just does not delete these tail entries during merge and compaction. And if you disable object versioning, you say, hey, I only want the latest version of the file. During merge and compaction, it would skip those entries while it is copying the data. Such a beautiful side effect of, now imagine this is a bug and S3 made it a feature that, hey, now in merge and compaction, I have to do less work, but I'll charge customer for the storage space that they're incurring. And you can have all the versions of your file that you have ever created on S3. Right? A really beautiful side effect of having log structured file system, writing it to a new location every time. You can access historical versions of it. Now, obviously, you need to maintain somewhere that this file path, or rather not file path, on S3 it is bucket and key. So this key is stored at this disk, at this file path, and so on and so forth. Right? For all the versions, you would store this information, and then you clean up during merge and compaction. So this is the information that you would store in some database. Some database. If you'd want to store it in some database, you would, because when you're supporting multi-versioning, you need to give them a way to access historical versions. So you need to store this information somewhere, that these are all the versions that you have. In most cases, you would say, let this do it. How many things with this storage rack driver do it, right? You need, this is your business logic. So you need to handle it on your own. You need to know where it is writing. It would tell you when your write is getting accepted, it would tell you that this is where my write is getting accepted. This is where I'm writing on this storage rack at this disk. You would store this information somewhere, which would allow you to go back and read it whenever you want it, right? And when you're supporting multi-versioning of a particular file, you would just keep this information handy, that these are all the locations where all the versions of my file is stored. So version 1 stored over here, stored 2 over here, 3 over here, so that you can access them at will. Right? Okay. Fine. So which is why I'm spending so much time on storage, because it is such beautiful byproduct of having this one constraint in place. Out of nowhere, we just got object versioning. Right? Okay. So now we know how merge and compaction happens. Now we know how disk space is reclaimed. When you delete a file, just this entry from this database is removed. So when during merge and compaction, it does not find an entry, so it would skip that entire file and move on and on and on and on. Right? And this is how your storage side of things function in case of S3, right? Okay. Okay, before we go on routing, let me take some questions so that this gets cleared up. Then we go into routing, then we go into hot partitions. Okay. Sitesh, you have any questions on the storage side of things that we discussed up until now? Yeah, Hemant.
Okay. So just want to understand one thing on this disk. Are we saying the location of where our file pointers are, that is managed by the software given by storage rack?
Yes.
Like it provides where.
Yeah. Correct. When you write it, you interface with this. It writes it to the corresponding hard disk and returns you in which hard disk it's stored and where it's stored.
So it is part of the same file system where I have these. It's out of one of the disks.
Correct.
It
Yeah.
is.
Yeah.
Okay.
Yeah.
Okay. I just want to understand this. Why? Because like last year, one paper came out of S3, which mentions this is now out of this disk.
I read that. I read that. Yeah. So it's both ways. So now obviously systems are evolving, right?
Yes.
There are new advancements being made, which is where I now added this part where storage rack can start abstracting a lot of things. Dell has put in a ton of effort into ensuring this.
Yeah. It is not still in production, that paper. Just want to understand.
But one of my friend who works at Dell works on this team. So that's why I know these details. That device never should. Yeah.
I got from that paper only. Now they are saying that LSM trees node where all the extendeds are there are out of that thing. Okay.
Okay. So they are, I am trying to recall that. Yeah. There's something mentioned of it. I'll still, but thanks for basically refreshing my memory. I'll go through it today once again. But thanks for that. Gaurav?
Hi, Arpit. So I think I missed it. Why do we store only 70% of the data and then skip to another disk?
Because this disk, why 70%? Because it is still accepting the writes that are coming in. Remember when we store a file, we define that, hey, I'm storing this file of this size.
Yeah.
Right. So when you are doing that, so it is still accepting the writes. If you wait until the last moment, the existing writes that are being sent onto this disk at this moment would be affected. Right. Plus, when you are merging and compacting, you need some extra temporary storage. Now imagine the way you merge and compact two gigantic hard disks, you may have to store some temporary information when you're writing it, right? Yeah. So if you are filling your hard disk to the fullest, you would not have extra space to do that, right? So the 30% buffer that you have would help you in your merge and compaction and would also help you continue to accept the writes that are in transit before the complete cutover happens to the next one. Clear?
Got it. Thanks.
Sure. Yeah. Rahul?
Just a simple question, like what would be the disadvantage of using chunked storage here? Like, let's just say we are not storing chunks in random blocks. We are just adding chunks, like it can be random hard disks, but it would be like a chunk, like we wrote a chunk to a file. Any another chunk in a particular hard disk will come after that only for a file.
Got it. So then your file becomes non-contiguous. So your access may become slower because now when you're accessing it, you're doing a lot of back and forth movement to read it. This is cheap commodity hardware. Magnetic disk, head movement would come in. So your random reads would be very costly. Got it?
Okay. Plus there would be hard disk degradation also, like
because plus now this is literal physical movement correct. So hard disk degradation is the correct term for that. Also called as basically the wear and tear of hard disk. Now the lifespan of your hard disk would decrease because you're doing you're making a cheap commodity hardware do a ton of work there. Right?
Yeah, got it.
Yeah. One last question before we move forward. Go on above.
here, but I had a question about log structured file system. So last time we discussed, I think, log
structured files. Yes.
Yes. So when it comes to file system, do we need like, we can't just sequentially keep writing to a list. We would need some tree-like data structure to support it. Like file systems are hierarchical trees, right? So
that's just meta information. So imagine those meta information is hierarchical trees, which is storing your directory structure, but the data is always stored sequentially one after another.
oh, okay.
Got it? So you still have tree, but it does not mean that that's how physically your files are laid out. Physically, your files are laid out one after another.
Oh, yeah.
But logically, they are arranged in a hierarchical tree.
Very similar to indexes in databases.
Very similar to indexes in data. Yes.
Got it.
Got it.
Yeah.
Great. Basically, Nitin, I'll take your question at the end. But yeah, this is the first time I've spent so much time talking about storage, but I'm really happy we went into depth of it. Like, why are we doing what we are doing? We now have answers to most questions. And obviously, I'm not a storage expert. I try to gather as much information as I could to, make it understandable. So I will have some limitations in understanding. Some things might be a little too abstract. But if I were this engineer, I would definitely have spoken about it. But things that I could pull off from papers, from talking to my friends who work in very similar teams, I tried to pull that off on the storage side. Okay. Storage done. Now let's talk about routing. Now, things is, when we talk about routing, very interesting thing that crops up is, how do we know, again, classic routing problem. How do we know where to go and look for the data? So I have API servers over here. So I have user API servers, and then I have a bunch of storage racks. So I have users, I have your S3 API servers, and then I have bunch of storage racks that I've stored. So now, how would you know where to go and read the data from? You would think that, hey, I need to know where I'm putting the data, where I'm reading it from. A classic case of routing. Let's say I got a request for a particular S3 bucket. Let's say bucket B1, key K1, and I want to know where should I write this request? Which storage rack should I write this request? Because I also need tenant isolation. I also need a way to tell that, hey, this storage rack or this set of storage rack are for this organization. This set of storage rack are for this organization. But you still want to have, but you cannot just assign one storage rack for one organization, because then what if the data, or what if that organization does not use it? It's waste of hardware. You're chopping down your margins, right? Which means you want multiplexing of, you want one storage rack to be there for multiple S3 buckets. But still, you have to ensure that you are still isolating the load of the customer. Like, both the problems are there. So now, first challenge that would come in is, how would you know which storage rack should I forward the request to? Right? A classic problem, a classic routing problem. So now, a way to do it is, you may think, hey, let me just use hash-based routing. Right? The most common thing that would come to your mind is, let's say I use hash-based routing, which is where S3 is a key value store. You just specify that, hey, this is the bucket, this is the key. You take the hash of it, find where you want to store, and you store it in that thing. Right? So for example, let me take concrete names so that it becomes easy. Let's say I have Amazon Prime. Let's say this is their bucket time, Amazon Prime. And for that, this is the key that they're writing. Let's say I have Netflix. This is their bucket, and this is their key. And then let's say Hotstar. I'm just using 3 completer names so that I can help you understand the importance of tenant isolation. Right? So you have Hotstar and they have key 3. Now, depending on the request that you got, that, hey, store this file, 1 GB file, somewhere, because S3 is abstracting it for you. You don't know where it would store it, right? These are S3 API servers. Now, how do you decide where to store this data? First point that comes to your mind, that, hey, let me just hash, like I have, let's say, thousands of storage racks. What I'll do is, given a bucket and the key, I would take the hash of it. I would find a storage node to store. and I would store it. Let's say you store it over here, right? So for prime, fortunately they have separate names. Super. Prime, and for key 1, I stored it over here. Then let's say for prime, in that same bucket, for Amazon Prime in that same bucket, I am having key 2, which I am storing over here. For prime, same bucket, I'm storing third file, which is being stored over here. And for P3, K3, K4 stored over here. And now Netflix came in, it's stored over here. Netflix came in, it's stored over here. Netflix came in, it's stored over here. So now you see that your one hard disk is now catering to request from multiple people. And there is no locality. Now, what's the problem with this? For example, if I am having a hard disk which is being shared by your Prime and your Netflix. Now, what would happen? If Prime sees a lot of load, the hardware is a physical, the hard disk is a physical entity. It has physical limitations, which means that if it gets a lot of requests coming in, it would not be able to handle all of them. So if let's say this Prime video was, let's say what the show that came in, what was that, Rings of Power or something, right? So let's say this was Rings of Power, very widely used, episode 1, everyone saw that episode. And here you have, let's say, Netflix show, pick any, some Netflix original, I don't got Netflix, let's say Sacred Games, or what was that? Let's say Sacred Games, not sure what that is, but I've heard something about it, whatever that is, right? So these two are very popular shows, part of the same hard disk. Now what would happen? When you're making a lot of reads onto that, the hard disk will start to throttle to very high, to very frequently accessed data stored in the same hard disk is affecting one another, right? That is bad. This leads to a hot partition problem. We would see ways to solve it. Hot partition problem is there, but you also see how heavy load on Prime can affect Netflix. So this is a place which tells you that, hey, we need tenant isolation. That somehow we need to ensure that load from one customer does not affect another. Right? You would say, "Arey, simple, na? Let's just handle it over here." Because all the request goes through your S3 API server. Let S3 API server throttle. That is there. S3 API server can throttle and will throttle. But still, if you're having two important things or two highly frequently accessed things in same hardware, that would still cause a problem. Let's say you do a limit. Let's say one customer can request 100 requests per minute at max, no matter what, right? But if those 100 requests per Prime and 100 requests per minute, both are under that constraint, but both are going to that same location, then that's bad, because one traffic from one is affecting another, which is where hash-based routing is not a good way to design system like this, because you are letting the control go in someone else's hand. What is someone else's hand? The hash function. Now, this is where you need to understand where you cannot use hash-based stuff. Routing, partitioning, pick your favorite, whatever it is, right? Now understand this very well. With hash-based routing, you take something, pass it through the hash function, you get something, and then you go and do activity on that. Be it API server, be it, in this case, it is storage. In API server, you go to that API server and handle the request, determining ownership that we spoke about consistent hashing last week, right? With hash-based, what happens is you rely on the output of the hash function, that it would do it uniformly. Yeah, it is distributing the data uniformly, but across everywhere it is doing it uniformly. So because it is not under your control that where the data would go to, it is wrong, because there is a chance where two highly frequently accessed things come and reside on the same database. This is wrong on many levels. So wherever you need tenant isolation, you typically don't see companies going for hash-based stuff, routing, partitioning, whatever you want to use, because it's not in your control. Ideally, what should have been there? You know that these two terms or these two things are famous. So ideally, you should be the one who should be defining that, hey, all the Netflix thing, let's be at one place. All the Prime thing, let's be at one place. That would have been best for you, right? This way, the load of one is not affecting others, right? So which is where S3 does not use any kind of hash-based routing, which include consistent hashing. Because consistent hashing, first step of consistent hashing is what? You take the hash, find one in the clockwise direction and you store it there. Suffers from this exact same problem. So consistent hashing, hash functions are no different, right? Because at the end, they are all determining ownership. So this is where, when you need, understand this, when you need control in your hands, you don't use hash functions. As soon as you use hash function, you are leaving it to the fate. You are leaving it to whatever output of hash function is. Go and write there. It's okay, right? But when you need that control in your hand, you don't use hash-based routing, partitioning, anything around hash-based. So a better way to design this is going with range-based routing, because it gives you the control that you need. That you define the range within this bucket, from this key to this key, this is where it would go. From this key to this key, this is where it would go. You define that range. Now you can do that balancing on your end, because now you are the one who are dictating that everything around Prime Video, or not really Prime Video, but everything around in this bucket, from this key till this bucket, this key, everything will go over here. At the end, on S3, your bucket / key is the unique key in which your data is stored, correct? So this is the factor on which you are doing range-based partitioning. And when I say range-based partitioning, let me use simple terms to help you understand what range-based partitioning is all about. So just to take a simple example, let's say I have keys from A to Z, right? And then this is bucket name. So now if I talk about Prime, it would be somewhere LMNOPQRP over here. So somewhere it would be Prime, then shows, then Rings of Power, then season 1, episode 1, something like this. So this is where that Prime wala thing would be stored over here. Right? This is where LMNOP. N is also over here. So Prime also over here, Netflix also over here. Right? You would have everything stored between Prime and Netflix over here. So because this is where you are defining a range of keys and where it would be stored on physical storage rack or hard disk, right? This is where it is being stored. But now you have this control. Now what you can do is you can split this. Let's say this is where a lot of hot partition is all about. A lot of traffic has come into. Right? Now I need tenant isolation. What do? You split the range, because all the Prime Video things is there in the Prime Video bucket, and bucket names are unique. You would always have this part where you can define a range and association to a particular storage layer. So for example, if your L2M or L2R is very hot and you want to split it, what you can do is you can have two nodes, create one node 1 and node 2, move half data over here, move half data over here. You can do it at physical side, at your physical storage layer. You can move the data here. It's a big process. That's why you don't do it often, but you need that control to pull that off, right? But if you want it, you want to move the data, it's easy enough to do it. In most cases, if you are arranging the data, because this way your data is almost sorted by the keys that you have, you can literally take your data and move it to other places just by moving the hard disk here and there and some data movement here or there. That's additional complexity, but you get the idea, right? So here, if my L2R becomes the hot node, I can literally split it into L2M and N2R in those ranges, right? And I just keep on splitting it by ranges that I have. And now, if let's say if there is L2L, very short range, but within that also, L say there would be multiple buckets and paths that are there. You can split within that, because now you have the control to where to split and where to move the data to. Right? That's the beauty of doing range-based partitioning. So the idea is wherever you need this things under your control, the way you are splitting, the way you are partitioning, if you need things under your control, you have to do it, right? So that's where you cannot leave it to the fate of the hash function. Okay? Wherever hash function says I'll put it, you take it in your own hands and do it that way. Now, a very good side effect of this is all the things you get locality. All the P's, like all the prime video file would be very close to each other. In 1 or 2 nodes, they would be part of it. All Netflixes will be close to each other. So now the load by prime video will not affect Netflix because everything around prime would be stored one after another over here. Or rather stored in the same object, may not be physically one after another because block structured file system, but they would be part of this similar set of hardwares, like a group of hardwares, right? And that's how you get with range-based routing or range-based partitioning, you get almost very good tenant isolation. Problem solved, right? This is one place where I always wanted to talk about that why you cannot use consistent hashing, because you are leaving it, the fate of yours, into the hands of the hash function, which you should not, right? Okay. Now that we are on topic of hot partitioning, let me talk about another way. It's a small detour from our discussion of S3, a small detour, but it's important to understand how hot nodes are solved. So this is how S3 does it, and almost all blob storage does it, which is why you go through S3 document, you see they use range-based partitioning. You go through S3 document, like their documentation, they clearly say that they don't use any hash-based stuff. They use range-based partitioning, and they arrange the data such that they get tenant isolation, right? So that load from one does not affect another. But just a small detour, not related to S3, but another way to solve hot partition problem that would come in handy when you're doing it. I think we have repeated this same thing in the past. I just want to spend one more like 5 minutes to this so that it's very clear in your head, right? So another way to solve hot partition problem is by how you create logical shards of your data, right? So in Instagram's ID generation, what we did is Instagram ID generation, we saw how Instagram had multiple logical databases and fewer physical servers, right? They created 8,000 logical databases, but they had 3 Postgres server to do it, right? So this is each of that database. And this is that server. Now, when a database becomes hot because there's a lot of load on one of the data or one of the partition, what you do, you take that partition and move it over here. Because it is partition, it is very easy to quickly take a dump of it. You don't have to go through row by row and see which one is part of this partition. You can literally take them in one shot and put it there. Just do a DB dump. Every database has a DB dump command, PG dump command, or MySQL dump command. Every database gives you very easy way to dump an entire database, right? Because they are stored together. You don't have to go through each table and then each row and then take it out, which is why people typically prefer this way of doing load balancing in hot partition case. So here you have 3 nodes in which you have these partitions distributed. If one of the nodes gets hot, you take that partition and move it to other node. You literally take dump, load, and resume. Classic way of doing it. Now, not just that. Elasticsearch, if you have used Elasticsearch, in Elasticsearch, when you create an index, you specify the number of shards that you want in that. The number of shards that you have is how in your Elasticsearch cluster, the data would be distributed. Using the Elasticsearch head plugin, in Elasticsearch, that is called as a head plugin, which is very amazing plugin. You literally can drag and drop a shard from one physical node to another physical node, and it would do that movement for you. It would dump it and then load it into another node and do it with almost no downtime, right? This is what Elasticsearch gives you. This is another way to solve hot partition problem, that where you can easily dump and load it to certain place. This is how you also tackle hot node or hot partition problem. Not related to S3, but a small detour to solidify that. Hey, there are 2 ways to solve hot partition problem. I just piggyback that discussion over here. So now what you can do is try this out. An Elasticsearch server. Try this out. Try this head plugin. See how you can do the data movement. It's very easy. Like this is something that I did literally as a fresher. What happened was I was part of DevOps team. We had massive Elasticsearch cluster. I had no idea what it was, what I was doing. One senior engineer explained what is happening and just sharing those things with you, right? So I broke down production twice because of that, but that's part of learning. So what happened is one of the Elasticsearch node that we had was very hot because we was seeing degradation in performance using metrics that it tells us. We know that we have to move this data to other node. Now how to do it? That's where head plugin we used which visualizes the entire Elasticsearch cluster on the UI. It looks very similar to this. You can literally drag and drop one and move it to other. The movement would happen. That is done by Elasticsearch on its own. We don't have to do anything, right? Elasticsearch takes care of dumping and loading and whatnot. It does that for us, right? A small script had to be written at that stage, but now Elasticsearch does it for you out of the box, right? But this is one way to solve hot partition problem. Right? I just piggyback hotpot, like multiple ways to solve hotpot because it's a very common thing to ask. Like, how do you solve hot partition problem? Now you know how to solve hot partition problem. First, ensure tenant isolation, range-based partitioning. Where you need tenant isolation, you go for range-based partitioning because you want control in your hand. You still got hot partition problem. This is one way to do it. You literally move the data from one to other so that the request comes on that side. Right? And you do it. Okay, we discussed that. Let me go through the sub. But this is exactly what we discussed. Let's scale storage and all, keeping it simple. S3 API we discussed. Consistent hashing, why we should not do that. Yeah, although it gives us minimal data transfer, but this is not what we need. We need a tenant isolation. That's the main concern. That's why we go for range-based partitioning. It does give you uniform data distribution. We saw that, but it may lead to that problem where multiple competitors are sharing the same underlying hardware. Not a good idea. That's where you go for range-based partitioning. And I talk about splitting, another way to solve it. Okay. Now we'll talk about API side of stuff. We spoke about storage. We spoke about routing. So if you see, we are basically coming ground up over here, right? We talk about storage. We talk about routing. Now let's talk about API side of things. Now here, there are a few very interesting things on how S3 or in general blob storages make such decisions. So here, we need to know, first of all, that when it comes to API server, you cannot, like a very basic way of building it is, I have user, I have bunch of API servers of S3, and I directly plug storage to that, right? Something like this. You may think that, hey, let my user request comes to S3 API server and it directly talk to the direct storage that are there. Now, the problem with this is the request can go to any of the S3 API server, right? So every API server is equally likely to handle any request, and it can directly talk to the underlying storage layer. Now, the problem with this is that in reality, I will have 100,000 hard disks, or rather thousands of storage racks. This S3 API server would need to know every single one of them, which is not feasible. Plus, every S3 API server is potentially can handle every single request. That is also a problem. Why? Because again, requests from Prime, requests from Netflix affect each other, right? What you want is, you want a clear separation of it. You want that the kind of request, the servers that are accessing the data from the underlying storage for Prime are different from servers that are accessing the data from the underlying storage of Netflix, right? So which is where you see how this is prompting everything around tenant isolation, right? Which is what the crux of this statement is all about, right? So what you do is you have defined a table called a partition map table. The partition map table stores that these are the partitions of your entire S3 range, right? These are the partitions, and this is where each partition is stored physically on the disk. right? You have that mapping somewhere, like you have huge enough racks to store that information, but you have this information stored that this is the partition map and this is partition. It serves from this to this, stored in this disk and rack, right? You store that information in your partition map table. Now this partition map table will need, like this partition map table, when we get a request, this is where we get to know that who owns this partition. So when we get a request, this is your actual storage. This is your partition server. Now, S3 API server cannot directly talk to storage because storage is very complex. Storage racks, interfacing with device drivers and whatnot. So S3 API servers, which are web servers, they are not meant to talk to direct physical hardware because there's a lot of abstraction that needs to go into. So who talks to physical hardware? It's the partition server that talks to physical hardware. Partition server holds the logic, who knows how to talk to physical hardware and get things done. Now, in this partition server, so on physical storage, the data is there, right? Storage rack knows how to access the data from a particular hard disk. But the partition server is the one who knows which partition does it own. So for example, in my partition map table, I have some partitions that it's just entries being made. The data is physically stored over here, multiple storage racks and whatnot. But when a request comes in for a particular partition, from the partition map table, we would know that which partition server will this request, or rather, this partition server handles partition from partition A to B. So everything around A to B goes to partition server 1, which in turn knows it is part of node 1. So it will go to node 1 and read the data and whatnot, right? So this is the kind of metadata that is stored in partition map table. Now here what would happen is from partition server 1, because I would know I got a request for a particular, let's say a S3 bucket that starts with letter B. I got to know this, it is handled by partition server 1. I'll make request to partition server 1. Partition server 1 owns that partition. It would go to storage layer, read the data, send it back to the user. Right. Now, if a partition server 1 is overwhelmed because it is handling multiple partitions, you can just move this over here to here, which is logical ownership. You just change this, that partition server 1 owns this partition. Partition server 1 now it does not own a particular partition. This is logical. This is not physical data movement. This is just logical ownership of a partition to a partition manager. So the thing is, one partition is handled by one partition server, but one partition server can handle multiple partitions. One partition server can handle or own multiple partitions, but one partition is with only one partition server. Right? Physically, the data is stored in your storage layer. That is now abstracted for us. Right? This is where we are talking about who talks to the storage layer. It's a partition server that talks to the storage layer. Who talks to partition server? S3 API server will talk to partition server. But which partition server will S3 API server talk to is determined by the partition map table. This way, on the compute side itself, there is a clear separation that primes with request does not interfere with Netflix request. Storage layer also that same separation. Compute layer also that same separation over here. Clear separation of responsibilities, right? Which is why range-based partitioning is such a beautiful thing over here, right? Okay. Now, these are partition servers, but now obviously these are compute. They can go down because now partition servers can go down, or rather, sorry, if let's say if one of the partition server goes down, someone has to know orchestrator flow that we discussed so many times in previous system. You put that in, that there is an orchestrator who is keeping an eye on partition servers. If one of them goes down, it would change the ownership of this partition to that other server and whatnot, right? That entire thing, copy, paste, works like that, right? But now this partition manager, now who is doing that? Oh, sorry, orchestrator, but I forgot about it. Sorry, my bad. Partition manager is doing that for you, right? Partition manager is the orchestrator. I forgot about it. Sorry for that. Orchestrator. So partition manager itself is the orchestrator who is doing that part for you into ensuring that your load is well distributed between the partition server. Partition servers are interfacing with the actual physical layer. And getting the data, sending it back, right? But now this partition manager, who monitors the partition manager, right? So you cannot have monitor for a monitor. And then who monitors that monitor? Another monitor. Who monitors that? So there has to be an end to that, which is where leader election comes in. So between the partition manager, just like how we had leader election in orchestrator, same thing over here. We would have leader election over here, that there would be one master partition manager. There will be multiple worker partition manager. The worker partition managers are actually checking the health checks of the partition server and balancing the load between them, while the master partition manager is managing the worker partition manager. If one of them goes down, it spins back up, right? But if the master partition manager goes down, one of the worker is elevated to become the master, right? This way your system becomes self-sufficient, right? And this is where leader election comes in. So again, I'll reiterate, leader election is there to make your system auto recover from failures without having any human intervention. That's why leader election comes in. So basically it's who monitors the monitor. When you have this question, understand you need leader election. As simple as that, right? Because the followers that are there are doing the actual grunt work. If leader goes down, another one becomes a leader. Classic how we work in corporate. When manager manages a team, if manager goes down, one of the team member conducts stand-up that day, right? That's it. Otherwise, manager, director will not come and take stand-up, right? There is no such thing like that. So you just promote one of them and then your team becomes self-sufficient. That even if manager is down, someone else is becoming manager for that time, takes that stuff, and on next day when manager comes back up, he or she resumes the responsibility, right? That same thing goes over here. So as I say, the world of computer science is very much influenced by how we operate, how humans operate, right? You would see those things in action over here. So this is where leader relation comes in, to build self-sufficient systems, right? Okay. Now, one very interesting design decision, and I'll just probe you all to think on those lines. Now here, the flow is, right? And now you folks need to tell me why this flow is very important and how it is one of the most interesting design decisions, right? It's very counterintuitive, but it's really good one. So here, the request from your user comes to your S3 API server, right? S3 API server first consults the partition map table to know that for this bucket, for this path, which partition server owns this partition. And then S3 API server talks to the corresponding partition server. Partition server then talks to underlying storage, reads the data, sends it back to the user, right? Partition manager is sitting over here, rebalancing the load between partition servers via health checks, right? If one of them is down, it does that. Partition manager manages the partition managers as well. The master partition manager manages the partition managers as well with the leader election and whatnot, right? Now, in most cases, we have seen systems where you would see something like this: request from user to API server, it goes to partition manager, then it talks to database, gets it done, forwards the request to server, it goes to database, storage layer, gets the data, sends it back. Why are we not proxying the request to partition manager? We typically never let other microservice talk to a particular database owned by some other service. But here we are doing it. Why? Anyone? We typically see this separation, right? Where we have one microservice, not because this is partition map table, typically part of a partition server and partition manager thing. We typically tend to have like, hey, my S3 API server should talk to this. Let S3 API server talk to my partition manager. Let partition manager talk to partition server and get the data and send it back. Why is S3 API server directly talking to partition server by consulting partition map table? Why? Yeah, Siddesh?
I think it's data flow.
Is it?
We don't want to see, you get the information, metadata information, which server you're going to write to and all of that. You don't want your whole data to flow through the whole system. So you want minimum house for data, and
But why do we do it in other microservices?
No, it depends on the data, right? Here it is a blob storage. You have
No,
gigabytes of storage.
Huge amount of data.
Yeah.
Size of data in transactional
Size.
systems, right? It's hardly 1 KB, at max 1 KB, right? It's typically rows that you transfer here and there. That's very minimal amount of data that you are doing. You can still afford to do that. Here, just assume that user is writing 1 GB file. You let 1 GB transfer to a partition manager, then partition server, then over here. That becomes costly. So that's not what you do. You talk to this database, get this partition server who owns it, sends data to the partition server, which writes to the storage. So you try to minimize the hop over here, going counterintuitive to what we typically do, that everything is a microservice and it goes through that. So this is at one place where all the theoretical concepts that we have is thrown out of the window, and we build system in a very practical way, because it's okay to share the data. Because what are the chances if schema of this database changes? Not much. It's a partition map table. It would show this partition server owns this partition and is present in this rack. That's all, right? Why should you even worry about that? Because it's not going to change. If it's not going to evolve, you can directly talk to the database, which just reduces the unnecessary hops that you have in your system, right? And this is what how really good practical systems are designed. Like, instead of just going by that very hard-bound rule, no, it's microservice. Everything has to go through server, no matter what. Consider the situation that you have at hand, consider the constraints that you have at hand, and then you design system accordingly. Right? Okay. So this is, and one more thing, the amount of data is there, plus the number of requests that this would need to handle will be same as number of requests a partition manager would need to handle unnecessarily. Why? Because if you let every request go through partition manager, data though is there, but apart from that, the number of requests also, because now this partition manager, if it goes through this is just a proxy. It has no business logic in it. Why to even have that? Let's just directly talk to this and get it done. Right? Minimizing the hops and reducing the size of your infrastructure to increase your profit margin is a way to make good businesses. Right? Okay. We talk about storage layer. Okay. This would give you that idea around who talks to storage layer. Partition server talks to storage layer. Right? Who talks to partition server? S3 API server talk to partition server. How we have designed the low-level storage details, we went through at the beginning of the presentation. That's exactly what I've covered. Right? Okay. Now let's talk about other things that people don't think about. Durability, right? Okay. So durability and integrity we'll talk about in depth. So data durability for S3 is one of the most important properties, because what you do on S3 is you write and forget. You trust S3 that because I've written a file, it will always be there, no matter what, right? So you are typically in the write and forget mode. So with data durability, which means that for you, durability is very important. That no matter if a storage node goes down, no matter if a rack goes down, no matter if your data center submerges underwater, no matter if there is natural calamity, like crashing everything, your data should still be there, right? This is the kind of guarantees companies have to provide, right? It is basically called as business continuity plan. This is what every company works for. That, hey, in case of a natural calamity, in case of disaster, in case of outage, in case of attacks, what is your business continuity plan? That no matter what happens, your business is always running. This is the first thing that your investors will ask you. What's your business continuity plan? When they do due diligence, when your company is raising funds, SRE head is typically asked this question, give me a business continuity plan. And you have to provide if you are leading SRE. I had written 3 documents. I know it very well, kind of stuff that I wrote, which is why durability is so important, because you cannot say that AWS gives you those guarantees. I had to take written format. I had to take written consent from AWS team, which says that they have the business continuity plan in place. And this is what we as customers have to do. And we attach it to our business continuity plan and share it with investors. It's all processes everywhere, right? So data durability is one of the most important things there. That no matter what happens, your data should survive, because data is everything for everyone. So what you do is when you are writing from a storage node, when you're getting a write request from S3 API server to partition server, from partition server to your storage layer, you're not just writing to one hard disk. You're writing to 2 hard disks at the time. This way, if one hard disk goes bad, you have your data in other hard disk, right? You may also choose to store to write it on separate rack. So if one rack goes down, you have your data written in another rack. You may also choose to write across data center in the same region. That, hey, I have 2 data center in Singapore. I wrote it in one, and asynchronously I write in another data center. Otherwise, you can also choose to do it cross geography. That I am writing one in Singapore, other in Australia. Right? So if Singapore submerges in water, I have data in Australia. Right? These are the things that you have to think about. So what S3 or any blob storage gives you, and obviously you can anyway envision that when you're writing at so many places, your write would be slower, and they are slower, right? But what you typically do is up until you're writing within the same rack, you typically are okay. So in most cases, when you write onto S3, you're writing at 2 places and not one, in 2 hard disks and not one, so that you outlive the hard disk failure. Right? So your data is still there. If one hard disk doesn't have it, other hard disk could serve the data easily. Right? That is durability. But if that data center goes down, you need to have data in another data center. If that another data center goes down, you need to have data in geography. That is asynchronous and chargeable. You have to pay huge amount of money for AWS in order to do this. So you don't typically do this for all the data that you have, but for most of the data, for all critical data, you have a copy across geography. You always have it. And it's part of your due diligence that your investors do on the company. That one copy of data has to be there in another region no matter what. And you may do it periodically, like per day backup or something like that, but it has to be there in another region. Because if one data center goes down, your business should still function. No one cares about anything else but business, because money is everything, everything is money. Right? Okay. So now you may ask this question that we talk about racks and all and hard disks and all, but what if a partition where I wrote the data, it got corrupted? You say, I have data in another rack. I can leverage it. Yeah, you can leverage it, but you can go a step further and configure RAID. You might have heard the term RAID, redundant array of independent disk, in your database course. If not from CS background, just Google RAID, RAID. You'll find what RAID does is there are multiple RAID formats. 0, 1, 2, 3, RAID 1, RAID 2, RAID 3, RAID 4, RAID 5, RAID 1, 0. Multiple of them, right? You can read about it, but the idea is that within the same hard disk, instead of writing to just one sector, you write at 2 sectors. So if one sector gets corrupted, your data can serve from the same hard disk from another sector. That is RAID for you in simple terms. So for anywhere, always remember this. Wherever you hear the term durability, the only way to guarantee durability is by making your data redundant. Any place that you can make your data redundant is a potential solution. So first level, when you're writing to a hard disk, you write at 2 sectors instead of 1, which means you are literally making your disk storage half, because if you have 1000 GB of storage, because you are writing at 2 places, you are only leveraging 500 GB. But it's okay. Data durability is important. You do that. That is RAID. You can do it 2 hard disks within the same storage rack. You can write across storage rack. You can write across data center. You can write across geography. So the only way to guarantee durability, 100% durability, is to have multiple copies of your data and having a simplest way to access them. Right? Depending on how sophisticated you want your system to be, you define those things. Some things would be free, some things would be chargeable. AWS typically charges you when you're doing it cross data center and cross geography. Within data center, it's typically free of cost, and it does it out of the box for you. Right? Okay. Now next, as a final thing, before I take question, is data integrity. Now this is something that no one talks about for some reason, but integrity of data is very important. Now imagine you're writing a file. You're writing a file from your user space onto S3, and the content of the file is BAT, right? But when you are writing over the network, a bit flipped. When a bit flipped, your B became a C. Because then just binary, the edit distance between B and C is just 1 bit. If that bit flipped, so instead of writing bat, you just wrote cat on the disk. And now when your user reads it, user would read cat. Say, I never stored cat. I stored bat. Where is my bat? Right? Which is where maintaining integrity of your data is really important across the layers. So what you do, the only way, not only, the most common, most performant way of doing integrity checks is using checksums. So what you do is you have to ensure whatever you got from the user is exactly what you're storing on the disk. You are not storing anything funky on your disk. You have to ensure that. Now, the way to ensure that is by adding checksum to everything that you're doing. Right? So at every single layer of your writing. So from user to S3 API server, checksum is passed. S3 API server to partition server, checksum is checked. From partition server to disk, checksum is checked. From disk, when you read it, checksum is checked. From partition server to S3, checksum is checked. From S3 API to user, checksum is checked. Even on user AWS SDK, checksum is checked. Even in HTTP request, checksum is set everywhere, because data correctness is very important. What you stored or what you think you stored is what you should definitely get when it is returned to. You have to ensure it, especially for a use case like S3, because it's a source of truth for a lot of things. You cannot just corrupt the data, right? So data integrity is really important. I was like, but hey, Arpit, if I'm doing checksum check for so many places, wouldn't it be slow? No, it's not. Checksum is simple. 32 bytes at a time. You process it. You XOR. That's the simplest way to do checksum. Like you continuously take XORs of 32 bytes. You read the data 32 bytes thing, or a batch of 32 bytes, and you keep on XORing it one after another. So it's not really expensive, but it is much needed for you to have your integrity check. So in case if integrity fails while storing the data, you would reject the write and say, "Arey, write failed, please retry." Right? But you have to ensure that what you're writing is what your customer thinks it is writing. That is integrity for you. And you have to ensure that. This is something that people overlook. When we design systems, we never think of integrity. We never think of checksum. We never think of data correctness. But these are very important things when you are designing an actual system. Right? Okay. So where did I get all of this information from? The first source of information for me was this paper, which I would highly recommend, and which is why the names that I gave was very weird. Partition map table, partition manager. I typically don't use those names because these are taken as is from this paper called Windows Azure Storage, a highly available cloud storage service with strong consistency. Read this paper. Given that we have covered this part, it will become very easy for you to read this paper. But S3 has not made their information public. Windows have, Azure Storage have. So I use that as a reference to cover it because I've never built S3. So I don't know what it is all about, but I try to gather as much information as I can by writing quick prototypes, talking to my friends working in similar domains to gather that information. But this is the best that I could offer at this moment. But I'm sure I do have some gaps in my knowledge, which I'm constantly improving on. And hopefully I'll find something new to add in the future. But read this paper, Windows Azure Storage, a highly available cloud storage service with strong consistency. You'll get an idea on how that, and this is exactly what like Windows version of S3 is. Right? Another paper that I would want you to read is this, Building a Database on S3. This is actually the name of the paper. Right? Building a Database on S3. This would solidify your understanding of how to make things queryable on S3. Like how we did with word dictionary, something very similar. There are very interesting hacks over there. So read this, another paper. Third one is a blog post. There is also a paper on it called Scuba by Facebook. It is Facebook's blob storage. Facebook has its own private infrastructure blob storage with the used to store media files and whatnot. They also have a paper on this. So read this paper to build a very detailed understanding of S3. These two to build S3, these two how to leverage S3. Right? And one book that is great for you to understand database internals is called Database Internals by Alex Petrov. One of the best books out there get a copy, read it through and through. You will love it. He has covered some amazing details around most commonly used databases in very much in depth, right? So go through this book called Database Internal. It does not cover relational database internals around query optimization phase and whatnot, but it still covers a wide range of databases and things you should know about it. It's pretty brilliant book in any case, right? Highly recommend you to read that book to build a very detailed understanding of databases. Right? And yeah, this is all what I wanted to cover as part of S3. Folks who may want to drop off, feel free to drop off. I'll take questions and it will be all part of record. Go on, Raj.
Arpit, I had so many questions. I forgot some because of in the content. I'll try to remember and ask again.
Yeah.
But I mean, if you go reverse manner, the replication part. Now here we thought that we were writing on a sequential basis in the rack with the head moving. The question which came to my mind is if you want to replicate in the same rack the data, you have only one currently active hard disk on your writing, right? How would you replicate to a different disk in the same rack, the data?
No, so the head movement is not within the rack. Head movement is within hard disk. You can still issue 2 writes on this thing.
But head movement was like the active disk, right? On which we are writing.
Yeah. So now you have 2 pointers, right? One is primary, one is secondary, and you write it in 2 places. Correct?
Okay, 2-pointer thing was not okay. Okay, so second thing was the hot key partition thing, right? So you told that if so you told that if the node is like hot, you can move partitions. But how would we know which partition to move?
Metrics,
logical partition.
Metrics. You would know which one is causing the problem. You would have analytics on top of it, right? You know for which key are you getting a lot of requests.
And then whatever partition is belong to, you just move
you
it.
need observability. You need to make those. So whatever system you are building, you need very high level of observability so that you know what the problem is.
So you remember I asked you the question the first or second week that what is the actual formula to sharding, right? So this is the formula. You observe, you have a metric, and then the metric is the source of truth for you to balance things out.
Correct. Because unless you know, unless you know what's causing the problem, you cannot fix it. You would just be fixing random stuff, right? So that's where observability is really important. In this case, assume that your request logs are that thing, because your request log would contain that, hey, for this key we are accessing it. So you have that observability that how many requests one S3 bucket is receiving. And you would get, okay, now this S3 bucket is a pain point, so I'll take this data and move it to other place.
Okay. So before we move from this slide, durability means like we thought about sector level replication and node, hard disk level replication, but then eventually data center can go down, as you told, right? Business continuity plan. So at least we should make sure that at least one separate location the data is actually replicated, right?
Yeah.
You don't act back.
It may be per day. It may not be very frequent. It may not be like every write is going in like everywhere, but at least once a day, complete backup of your database into a different region is something which everyone prescribes.
And the writes to, let's say a user is uploading a file, right? And you're replicating to a different data center. Let's say the replication part, the write part, again to a different data center happens exactly the same way as it happens to the primary one, right?
Yeah. But it will happen after a delay. It's not real time.
No, yes, right. And then you have to maintain a map also. Okay, what is the primary, secondary partition tables?
Partition and whatnot. Yes.
Okay.
And as soon as you add durability complexities, a lot of things that we discussed changes. And now a lot more additional information you would need to store. Right? All of that is stored. Yeah.
And the point around partitions, right? Key partitions. So bucket and the key is the input on which we actually put a range, right? We put range. Now, if you take a real life example, bucket ID is like a bucket for a particular user, right? Who creates its account basically.
Yes.
So if Netflix has its own account, let's say one account to be simple to have simple observation. Now Netflix has so many videos, right? So many videos are there, right? In real example. So if it is like the file is the key, right? So if the file is the key, then there could be, the starting point would be like Netflix, right? So N is the starting character. So you did a character alphabet based partition. So that means the Netflix itself has so many movies, right? So N itself has so many, so much data, right? So if you end up in a situation where one alphabet has a lot of data to
you go within that, right? You go NA, NB, NC, ND.
Right. Yeah. That's what the person tried to ask.
Right.
Yes,
you go and which is I said it's not
So
that I
try-based approach,
simplified.
NA like try-based approach.
Yeah, I simplified it with single characters, but do it at that path level where you'd want to draw that line. That this is where this would go, this is where that would go to other partition. Right?
Right,
But
okay.
because you're putting it
Mm.
all alphabetically, what happens is all things belonging to the same bucket would stay closer to each other.
Yeah, that I know.
Hmm.
Locality of reference. The last question here is the place where we're trying to write it on a node, right? On a disk. Basically, you can go to the page where we're writing the data to the disk. The first slide, I think, we were
This one, writing data to the disk.
where
What
we
table?
have. So we were trying to write data to a disk,
This?
right? So disk 1, disk 2, we had the headers. No, not the previous one to this, not this one. Okay, let's take any example.
Yeah,
Where
take
you have
any
array
example,
of,
that's fine.
yeah, even here itself. Now let's say you said that no, now you introduce a concept of 2 pointers. Let's say we have 1 pointer which is active disk. Now you said that okay, let's say we have a file of 10 GB and we know that okay, our current disk size is 90 GB, and by the time the next write comes 100 GB. 100 GB is the size of the disk, and then it will be over, and you just move the head to a different disk, right? You calculate that. But in point of time, let's say 5 GB were written, and then for some reason the write failed, the upload failed basically, and your header at the point header has moved, right? Now how would you do a fault? How do you recovery? I mean, how you will ask the uploader to upload the file again?
That's what happens
then
at this moment. That's what happens also at this moment. And that is where to reduce that, you can do chunking and whatnot. Those are enhancements that you can do.
Okay, yeah, chunking means the inode also, right? If you have multiple small files, the inode actually goes out, exhausts out, right? So
yes, trade-offs, right? You need to know because if you try to solve one, you would lead into another problem. So either you ask the customer to re-upload that part. If it's small enough, that re-upload would work, right? But in any case, you can still write it as an exception. You can still write to the old thing because you still have 30% of extra space to continue that write. You can do that.
Yeah. Okay.
Right. Now these are very, very intricate details of it. When you implement, this is where you would discover that part. But it's good that you folks are thinking on those lines. Now think of implementation, which is where you see far more challenging stuff there. Right? And it's not difficult to prototype. You can start prototyping it. You would start stumbling upon very interesting edge cases. So you may think, "Arey, now how do I handle it?"
The fat case is like you are uploading tens of GBs. Now 10 GB is like standard we discussed. It's 100 GBs, right? So network thing also you have to break down files in chunks and then send out.
Yes. And now if you look carefully, now this chunk is just an extension to this. Instead of storing one file of this part, you implicitly chunking it and storing it so that your user does not have to resume the user can resume the writes from the last point. Okay. Now that is an extension, but in the first version of S3, they would definitely not have built that. But in future version, they would have added that feature.
But Arpit, if in case you do a chunking, so you have a chunk manager as well, or the partition manager takes care of this. I mean, you have a DB.
Yeah, that's implemented. Like, I don't know. I have not put some thought around it, but I would let hard disk tackle it, and maybe in partition in the file, I would have meta information around what all chunks are there, where all are they placed, and whatnot. Because now I have to still provide a way to seamlessly access the entire file.
You have to accumulate all the chunks, right? And you replicate also. So all those things.
That is different. That is, you are going in very different direction now. If you are still combining all those chunks and storing it in one place, that also becomes a problem then.
No. Chunks would be in different places because anyway, I mean, not different places. They have to be in a single place. Chunking is just basically to reduce the network load and resume from the point you want to upload the file. Okay.
Think about it. It's more complex than what we can discuss in 5 hours. It's much more complex than that, right? Okay. Mohit?
Yeah, so Arpit, how does the read path work? Like, I think we discussed in the storage racks, you have basically a head pointer, which is just keep on appending items to there. But let's say you get a read request for some item, which is now past the head. Now, like,
no, it does not mean that, see, your head can always move back and read stuff. Random reads are allowed, random writes are not. S3 is not a read-heavy system, FYI. S3 is a write-heavy system. It's very contrary to think S3 is a read-heavy system because S3 in reality there is very high amount of data which is being written and very less data which is read from S3. S3 is a write heavy system. So in S3, the write to read ratio is huge. The number of writes are more than number of reads that you make on S3. Right? So when you are in such situation, in your read path, it's not always the case that I would only like, because my head move forward, I cannot go back. Your random reads are allowed. And similar to what we did in Bitcast, where we were still doing random reads, our head used to move back, read the thing, send it back to the user, and then move forward. That's what we do over here. Now, because we moved from one hard disk to another does not mean we would not read from previous hard disk. Reads can still go to the previous hard disks that are written. Right? That would still be there.
And like the merge and compaction part, I think that would change some of the mappings of where the data resides. So
and your partition map table needs to be changed.
Yes, as part of that process. Okay, and when you say that, like, I'm still not able to digest that when you say that S3 is more of a write heavy system than a read heavy, like most probably you would be getting, like, you'll be issuing a lot of gets on S3, like be it configuration data, be it static data, be it file, like you would maybe write maybe some database files once, but you are reading it quite often. So if you could maybe elaborate.
But are you see the amount of data you have written on S3 versus amount of data you read from S3? There would be few files that you are reading more often. In most cases, there are smaller files, configuration files, as you gave an example, right? When it comes to large files, do you read large files often? No. Right?
No.
You write a lot. There are few files that you are reading more often than others, but it does not make S3 read heavy database. Because the amount of data that is being written and the amount of data that is being read, the amount of data that is being written is more than the amount of data that is being read from S3. Because S3 gives you very slow reads. So it does not make sense for you to read it in transactional use cases. And in most cases, the high traffic things are transactional. Analytics is not that read heavy. Analytics is not that frequent anyway. Right? Because S3 gives you very slow reads, people don't use it to read things often, except for few smaller configuration files here and there. Right? So that is why S3 is a write heavy use case and not read heavy use case. You get it now?
Okay. Yeah, got it.
Because it's even when I was diving deep into this, I was going through, I think, S3's documentation itself. And I think they mentioned somewhere in the start that S3 is write heavy. I'm like, no, I'm reading so much from S3. But then I spoke with a couple of folks. We were just brainstorming on this. And then we found some paper, I don't really remember, 6 or 7 years back. We found a paper which was not 6, 5 years back. Yeah, 5 years back, 2018. Yeah, 2018. In 2018, I was going through this while I was in middle of that job switch. I was going through this and I found a statistic which had amount of data being written versus amount of data being read from S3. The amount of data being written was more than amount of data being read from S3. And that's when then we started probing and we found out that the amount of data in the organization that I was part of and the amount of data we wrote was much more than the amount of data we read from it. Which is why S3s are write heavy. People typically write and forget. In most cases, it's backups that you're storing on S3. And in most cases, you are like, obviously, there are cases where you're serving images, you are serving videos and whatnot. But what are the odds that every video is equally likely to be accessed? Take example of Netflix. 1 or 2 video very popular being accessed. Everything else is just sitting idle there, right? So it's very write heavy system, not a read. So a system is read heavy when you have 90:10 ratio for reads. It's not that much. For some files, yes. For most files, yes.
Yeah, and I think for media files, the CDN will also come into picture, like when the read traffic is there. So
yes.
Okay.
Okay. Siddesh, thanks. Siddesh.
Hey, Arpit. Yeah, I just wanted to discuss so this system that we developed has a few major limitations, right? Like one is the size of the file.
Yes.
Number. Sorry, I didn't get it.
Yes. So this is size of the file is the word. Yes.
Yeah, and second is the amount of data. Like I'm having harder time understanding that it being a cold storage, we are not deduplicating any of the data. Rather, we are actually replicating it. So a user's facing 5 terabyte data is actually getting converted to something like RF3 also. It's 15 terabytes now. So yeah, I was just thinking like,
Okay,
this seems a lot to me, because given that organizations are going to dump petabytes and petabytes, it's just going to get amplified.
Yeah, 100%. I totally agree with that. But that's the kind of guarantees AWS has to provide. If you are,
makes
because
sense,
if you delete the data, and if they lost their original copy of data, you don't have another copy of the data. Let's say, because it's a very common it's a very common use case where S3 folks get tickets like saying, hey, I accidentally deleted my data, can you recover it for me? It's very common. To be honest, it's one of the most common requests that the S3 folks get. One of my friend works in S3 team, and they analyzed this part, and they said that almost at one stage, almost 30% of requests that they got, 30% of support cases that they got was around recovering their data. That's when that they added into that part on the UI through which you can recover the data. Like you can see your recently deleted files and you can recover it from there. And which is insane, because it's so accidental to delete data and then you realize that I should not have done it, or maybe a bad script happened and you deleted it, right? So that's why having another copy of data is very important. Second, in most cases, people are now not using S3s to just dump their data, because data lakes are built on top of S3s nowadays. So it is not just one place to which is just like my backup. In a lot of cases where now companies are building data lakes on top of S3, given that now S3 is HDFS compliant, any workload that used to run on HDFS can now seamlessly run on S3. If it is HDFS compliant, people are just using it as their massively distributed storage file system. Entire data lakes are built on top of it. So now that is not just becoming your backup storage, but also somewhere you are relying your business analytics on top of it. Now your business decisions are being made on top of it. Having copy of data is very important now. Right? So, which is why they still charge you very handsome amount, 4 cents or 0.4 cents per TB is a decent amount that they charge. Or rather, 4 cents per TB is a very decent amount that they charge. Right? So they're minting money because of that. But we think we refer to it as dirt cheap. It is actually costly when you see the lifespan of your organization and the amount of data you are storing there without deleting.
Yeah. The moment that's the thing, right? Once you move it, it's very hard to move it out. Correct. And that's the trick. Yeah.
That's the
anyways, and then another limitation I felt was this system is going to be heavily fragmented eventually, right? Because once you start accepting gigabytes of files, that is where I was wondering to, like, initially
version compaction is there to solve the fragmentation problem.
But how much can, like, in the sense, that's what I was going to ask, like, is it solving per partition, or is it solving, like, do you do this, like, you actually, when you merge, you actually defragment the whole disk?
Create a new defragment the whole disk. That's what happens in version compaction. You're defragmenting the whole disk to get the maximum available space on that, and then you move the data, and then you reclaim the space, and then you basically reuse those space. You do that. That's why version compaction is a very heavy process in case of S3. Very heavy.
Yeah, that's another question was in this partition server. I have like confusion in this diagram. One partition server is it like a logical partition inside this rack space, or is it pointing? Okay,
it's a logical
and that
partition
is mutually
that
exclusive, right?
Mutually exclusive. So this partition is different from this partition. So one partition server can own multiple partitions. So which means any read request for a particular partition that comes in, it always goes to that particular partition server. And because this partition server owns those partitions, it knows how to read it from the disk. It reads it and serves it back. Right? And if this partition goes down, we move this to other partition server. So this is just a logical ownership of a partition. Physically, data is stored over here.
Got it. Okay. Yeah. The reason I asked is because we did not go into, like, this system is simple enough to not go into concurrency. So
exactly. Yeah.
And so you have kept it mutually. Good.
Yes. And we don't need it to be concurrent anyway.
We don't need it. Yes. Yeah. But there is one problem though.
Yeah.
one problem that maybe it's a complicated problem, but when we move partitions, right, biggest issue is like generally now 2 servers, there is an intermittent time when you may have it accessible, 1, and 2 is there could be some stale requests, which got, yeah.
But files are not getting updated. It's read only.
Oh, I see. When you, oh, perfect. Yeah, that is what I was missing.
This is very important. S3, that's what I say. S3 is write and forget. You are not, it's not a transactional DB in which your data is being changed on the fly. It's written, it's written.
Simplifies it. Yes, it simplifies a lot.
Exactly. That's why it's like a lot of things that we think, array, how to handle this? S3 does not need it. The problem with S3, which is why I spend a lot of time talking about storage side, because everything else is oversimplified for S3, given that does not have to care about concurrency. Once file is written, you are not updating it. Any updates is a new file.
Yeah, that's also a huge amount of problems. Yeah, and another thing is this: when we talked about replication, I think I don't know if we missed it, but this everything needs to be replicated, right? Even your metadata table needs to be replicated. Yeah,
so this partition map table itself has replicas and whatnot. All those complexities, right? Everything we studied previously, copy paste over here. How do you ensure uptime of this database, failovers and whatnot? Everything fault tolerant.
Okay, yeah, good. Thanks.
Yeah. Yes, Nitin, go
on. So I have a question on the very first, the thing that we discussed, the data rack, right? So I'm thinking in terms of how are we storing the file? Like what kind of file system we are using? What kind of, like what's the maximum limit of per file? Okay, so first of all, can we shed some light on like what should be the file system over here?
Log structured file system.
No,
there's a file system we are using.
Okay, like what's the
maximum? EXTFS, are you talking about EXTFS, BTRFS?
Yes.
So similar to that, there is log structured file system. There are 2 very popular implementations of it. I really forgot the name of that. But you are formatting the disk in a log structured file system. First thing, right? Now, the limitation of file, that's a brilliant question. Like FAT files, like if you have a FAT file system, FAT file system, the limit is 1 GB. You cannot have more than 1 GB file, right?
Correct.
Right. For NTFS, it is, I think, 4 GB or something. And for EXTFS, it is 16 GB or something like that. On S3, I think S3 tells that the limit is 1 terabyte or something. Obviously, S3 internally does chunking and all. But let's say we don't think of chunking at the moment, right? Then we'll introduce the complexities of chunking. Let's say we don't think of chunking at the moment. Now, what we can do at this stage, let's say we define a limit. We define a limit that, hey, my file cannot be more than 1 GB, hypothetically, right? So which means that whenever a write request comes in, as I said, when a write request comes in, you have to tell on this bucket at this path, I want to write a file which is this big. You may not provide the entire bytes, but you are reserving the space there, right? This is what you do in your write operation, S3 write operation. Either you send the entire file or you request S3 to reserve a space for you, correct? In multi-part upload, right? Okay.
Correct.
So now, up until now, what you have is, you have now reserved some space to store that file. Let's say this is maximum file 1 GB, which is allowed, right? And then you write data over here. You say that, hey, this is the chunk, write it at this offset. This is the chunk, write it at this offset. So it gets written over here, and then you complete the file. This is how your multi-part upload works, right? Now, S3 can give you like on this file system. So there is one limitation of file system, that how big this file can be. It depends on which file system are you using. Let's say log structured file system, hypothetical example. Let's say it gives you a limit of 1 GB file. But I need more file. I need big file. So let's say if S3 supports, I'll support 1 terabyte file. You can have on S3. So what S3 internally can do is S3 can accept 1 terabyte file, but store it as 1001 GB files.
Okay.
And maintain this metadata. So S3 has a limit which might not represent the limit of the, I'm so glad you asked this question, which might not represent the limit of your underlying file system. Because log structured file system cannot block a huge chunk of file, right? So this is where your inherent chunking comes in. And they would need to anyway maintain that this is file path 1, 2, 3, 4, 5, 6 stored at this location, maintained in inode, but together it is one big file. Right? So file system limitation might be 1 GB, and I'm just giving random example, but S3 can say I can support 1000 GB file as well. Right? But then how S3 would be implementing it would be something like this.
Okay. Yeah. Another thing, like one kind of like suggestion. So basically, let's look at this rack. Okay. And what if we split our file, whatever size it is, into smaller chunks and distribute it across the HTTs, and so that we can implement a parallelization among these HTTs. So can we do that? Like, what's the pros and cons of that?
Great question. Why do you need parallelization?
Because HDTs, I mean, let's say one 1 GB file is being there's a request for one GB file for read. Okay, the whole load would be on one particular HDT, and it will sequentially read it and serve it. But what if we split it into 10 chunks and split it across the whole HDT racks? Okay, so HDT 1, 2, 3, they will be parallelly reading it and serving it to the partition, whatever you call, like the partition computer, which is on the rack.
Yeah.
So parallelly, all those chunks will be, read, serve it to the partition computer, and then it will be assembled and sent it to.
Okay. Now, my counter to that is simple. Is S3 a read-heavy system? Not
let's
really.
say.
No, wait. Is S3 read-heavy system? No. Right? People are not going to read frequently huge items because huge cost is involved on that. Right? S3 is a write-heavy system. So that solves that problem partially. But in any case, you have multiple copies of data stored. If you want parallelism, you can leverage multiple copies of data that you have anyway stored. Durability.
Yeah, but that's stored across different regions, right?
No, not regions. Even racks, within rack, within hard disk, within rack, and within data center. You have that.
Okay.
Right? You can leverage that. If you need little faster reads, you can leverage parallelism using durability because you have multiple copies of data. Right? You don't need to chunk and store everywhere, because that makes things much more complex. Because now imagine now for you to read this entire file, you have to read different regions from there. And now user is waiting for it. Reading from multiple places will take time. Let's say user is sequential, and in most cases, our file is on S3 is always sequentially accessed. Right? It's not parallelly accessed. It's always sequentially accessed because you are not sending everything in one response. Correct? Imagine S3, the way you are accessing the file, you are asking to download the entire file. You are asking to download the entire file. You are iterating bytes by bytes sequentially and then accessing it. Right? That is very common. So you always optimize for common use cases. For anomalies, you don't optimize your system for anomalies. You find hacks to solve anomalies. This is where, if you want parallelism, then S3s can do parallelism through the durable copies of data that it created within the hard disk, within rack, within data center. No more latency is there. So you have 3 places where you can read those same things in parallel if you want to. Right? In any case, it's not read heavy. So it's okay. Right? Does that answer? But I'm not stopping you from implementing this. If what you're doing is you're building a read heavy blob storage system, if market needs it, you build it. Yeah, in that case, you would do what you suggested.
Let's say I'm building a Netflix, then this case of
no Netflix CDN se serve hota hai.
Let's say I don't have that CDN technology and all. Let's say I'm solely relying on this S3.
So then you create thousands of copies on S3s and then basically balance the load between them.
Okay, so multiple racks are serving different chunks.
Not chunks, same file copied at 10 different racks, and you're balancing between those racks.
Okay, got it.
Right? I would always find other hacks rather than chunking and storing, because I want that file. Because even in case of movies that you take as an example, the way you will be accessing the movies is always going to be sequential access. If you're storing different chunks at different places, that is additional overhead for you to do that computation. Which chunk is stored where? Now I read till this byte. Now I have to read the next byte. this, but the first 5 bytes are in this chunk, next 50 bytes are in that chunk. That is additional computation. Keep it very simple. Got it?
So we can, so basically we have a ample of storage. We can recompute this data and save it in the partition server.
Then your partition map becomes big. That additional metadata itself becomes huge for you to access it.
Yeah, so we are like kind of trading off the memory utilization over the time complexity.
But this is not, it's not, I'll give you an example. Wait, I'll give you an example where it is there. And I'm not denying your answer. Your answer is there. I'm just proving you to think on different sides. Wait, let's say you chunk the file into 10 bytes. I'm taking simple example. Let's say you chunk the file in 10 bytes. So this is 0 to 9. This is 10 to 19, right? Now you are iterating this file byte by byte, rather 3 bytes at a time, or rather 4 bytes at a time, right?
Okay.
Now what would happen? You are reading 4 bytes at a time. You read, now what you would have, you would need in meta information that this is chunk 1, which is stored in this file over here, which is of 10 bytes. This is chunk 2, which is stored over here, right? Now we are iterating file 4 bytes at a time. Now what would happen? You would read 4 bytes. You read 0, 1, 2, 3. You read it, right? Then you read next 4 bytes, 4, 5, 6, 7. Done over. Then you read next 4 bytes. Now what would happen? You would have to read 2 bytes from here and understand that, hey, I'm missing 2 more bytes. Then you would go to this database and find where the next chunk is. You would go to there and then read 2 bytes from here. Correct? This is additional complexity. Because now when you are requesting to read a chunk, and now on S3, you can provide this, you can fire a query that says from in this file, read from this offset these many bytes. It's a very common use case on S3, right? Given that you can fire queries like this on S3, which means there is a possibility where your request can span multiple chunks. Now you have to do this computation that this offset is present in this chunk at this path and this offset is in this path. So I have to read these many things. Not worth it, right? Because it's not a read heavy system. What you're proposing is good for read heavy systems where you're doing micro reads, and micro read does not mean just very small byte level stuff. I'm also talking about MBs, right? When you're doing micro level reads, that is good enough. But when you're read heavy system, this is not a read heavy system. Blob storages are write heavy systems and not read heavy system. To do this, to get over this complexity, just create multiple versions of the file because hard disks are cheap. You get creating multiple copies because files are not getting updated, right? Files are completely written every time, which means that you create multiple copies and extract parallelism if you want to, rather than doing this part. This is much more complex. Keep things simple.
Okay, got it.
Right? But what you're suggesting is something that is doable for read-heavy transactional systems. You can like read-heavy transactional blob storage systems. You can do that. You can do it.
I was kind of thinking in terms of Netflix streaming, video streaming. So, so another question is that, so what if, so in our system, let's say one particular hard disk rack becomes hot. Okay, a lot of requests are being directed towards that only. So let's take an example of Netflix. There's a movie 1 and movie 2. They both are very frequent. I mean, they're both are very popular, and a lot of people are watching it concurrently, parallelly. So both of them movie resides in one hard disk rack. Okay, so do we have to implement such kind of system that balances the balances this thing? Let's say if 2 of the movies becomes too hot and they should be shifted to another rack so that the one hard disk rack shouldn't crash.
You typically don't do that. Why? Because in real world, first of all, there is CDN to serve it, and I'm not just basically dodging the problem statement. But you typically don't do that in real world because you have CDNs to do that. But if I still assume that, let's say all requests coming in onto S3 to do it, right? So in that case, S3 anyway has a limit on the number of requests you can make per access token, or rather per customer. It would not go beyond that. So you are playing in this limit. You are not saying that, hey, whatever request I get it, I'll handle all of them. Because you are playing by the constraints that you have. You are S3 designer. You can put the limit on the number of requests that you would handle. And now if other system wants to access you, you say that, hey, this is our limit. We cannot go beyond that. You figure out another solution. You don't have to adjust to every single request that is coming.
I'm talking in within the constraints only. Let's say there are 10K concurrent.
Then you would define the constraints such that it would never become hot.
No. That's correct. I mean, we have a constraint 10K, and we have, let's say, 10 racks. Okay, and one of the rack is serving like 7K or 8K, the 80% of the load, and other 9 racks are not serving that much. So do we have to implement such a mechanism?
I'm talking about
that
limit per rack. That's how you would define it. You would define per key limit. Per key limit, how many times can you access it in a minute? Got it? So S3, if you go to the specification, they have per key limit as well. That per key you can access these many times, like these many data ingress. It's in GBs, the dispatch of data you can take it from. And that is derived from the hardware limit that they have, the hard disk limit that they have. Right? Otherwise, you can, if you want to ever build it, you put a cache in front of it, which actually becomes your CDN, to be honest. Right? Those are other ways to build it, but you can extend the system the way you want. But typically you don't cross. See, as soon as the hardware is added, you cannot go beyond that. Right? Whatever the hardware limit is. But if you'd want to move that as an exception, you can copy the data and move it to other hard disk and then serve it. But then you need to maintain that additional metadata, which says that which lies. Because now you're breaking range-based partitioning by moving data into some other place. Now that's the risk that you are taking. Right? So now that is additional metadata that you are storing. Not needed. Right? If they want to use it, they find other ways to do it. Got it? So you define the constraints such that your system doesn't break. And your foundational rule that you started with, it doesn't break. But if that customer is big enough, you put a cache in front of it and cache all the data in some other storage and serve it as an exception, but not as a general practice. Right?
Okay.
See, you are trying now with this, the kind of things that you are putting in, it is making S3 into a transactional database. Right? Don't think on those lines now, because S3 is meant to serve different kind of problems. And you would define your own constraint. If you go through S3 specification, you would go to know the kind of constraints that it imposes. You cannot breach that. Right? But everything that you said, you can make it as, you can put the data into other hard disk and have a mapping that stores that, hey, this file, all this present in this stack, but this file is now present in this stack. So instead of going for range-based partitioning, you go for range-based partitioning for most cases, but for exceptional cases, you go for static partitioning. You say that, hey, this file is present in this path, this file is present in this path, and this hard disk. Right? So you first check your static partition map. If it's there, good enough. If not, you go for range-based partition. And then you access the file. That's also a problem. Correct? Okay. So exceptional cases goes to static partitioning. You first check that. If it's there, you go with that. If not, you fall back to range-based partitioning and you just access the file the way. Cool.
Okay. Another thing is that can we talk some numbers over here, like about a whole system, like how many concurrent requests can it serve? Like
it
just
depends. I've not built SA. I don't know the numbers. It depends on how fast your hard disks are. Right?
Let's brainstorm on this thing, like just like we do it in an interview, like we are given a problem statement.
Not at all interview. Go on. Ask me a random question without saying interview.
No, I'm not saying that. So that I mean that. So why I'm asking is that we would like it will build our intuition, like how much
ask me question. Ask me questions. How would you start? How would you start with that? Without you knowing the throughput of your hard disk, you cannot start with a number. What is the throughput of this hard disk?
I don't know, like what kind of model and all we are using.
Exactly. Unless you put the load on it, you cannot tell. Right? You need to put the load on it.
But this is the bottom
of this hard disk.
This is the bottom up approach, right? we are thinking from the lower level, like what's the throughput of hard disk, and then we are building up the numbers to the end. Let's say we are to our end user, we are saying, let's say we have a contract with our user that we are gonna serve this number of
without
parallel
knowing a
requests.
physical limitation, you cannot define a contract. You cannot just claim I would go for 1 million requests per second where your system cannot handle 100 requests per second, right? It's always bottom up. It's never top down. It's never that I would want to handle this many requests and then I would define this. It's always what your physical hardware limitation is, which then propagates upwards. And then you say, okay, this is what we are guaranteeing. It's never top down. In storage systems, where your underlying thing is storage, the hardware comes, like hardware limitation comes at the cost, right? You start with that and then you move up. So in log structure, you assume whatever throughput is. Let's say 32 GB per second is what you're getting from your hard disk as a throughput. You start from there. If your hard disk is giving you 32 GB per second, which means you cannot go beyond that on that hard disk. 32 GB per second is what you start with, which means on an average, if file size is, let's say 1 GB, how many files you can read in 1 second? 32 files in 1 second, right? And then you move upwards and then you define your boundaries, right? You start with it. Assume it's 32 GB per second. It's roughly, it's basically the network bandwidth, but assume that it's 32 GB per second because you anyway have to read it over network, right? Start with that. And then you say how many files you can read in parallel, right? You may say, let's say 32 files in parallel. 32 files in parallel, how many requests you can handle? So assume that your average request size is of, let's say, 100 MB. How many requests you can handle in parallel? You do that division, and you come up with that number. And then you know how many things you can serve in per second. Now, multiply that with number of storage racks that you have, the number of distributions that you have. You would be that would be the guarantee that you would provide to your user, correct? It's always bottom up. So 32 Gbps hardware limit, start with that, then you can compute those numbers.
Okay. But we also have to, this is a, we also have to make, like, think about the network bandwidth between.
That's what I said, 32 Gbps is the network bandwidth.
Okay. Okay, I thought it was a SDT throughput.
Why I put that? Because hard disk can read more, but if you cannot send it over network, then what's the job of it? Correct?
Correct.
That's why I went with 32 Gbps. Hard disk can read much faster than that. I went with 32 Gbps on a high throughput network. Because it is capped, because it is bottlenecked by network. Correct? That's why 32 Gbps I said.
And also we have to take in consideration about the partition servers, like at each and every layer, including the network bandwidth and the throughput of each and every system. Like how much time does it take for a network partition if there are concurrent request of, let's say, 100K, and so how do we build that intuition? Like,
yeah, that's the division that you would do, right? Because now you have to define the access pattern of it, that you cannot access these many things at one shot. You assume that, hey, this client would make at max 100 requests per second. And then you cap it at that and see if you are able to sustain that load or not. Assume, like, you have to make a lot of assumptions when you are doing this. Start with that, play around with it, spend some time. We cannot do it live. Spend some time thinking about it. More than happy to discuss tomorrow, right? But go through that. Start with 32 GB per second as a limit of what you can read from your hard disk to your partition server. And then now everything is just compute. So now you can define what your per token access limit should be. Cool. Start with 32 GB per second. And then you define those constraints that how you are allowing people to access your data. How you are allowing people, like what are files they can access, how per file limit, per bucket limit, per partition limit, right? Per access token limit. You define that, because once you know your numbers, once you know your unit tech economics, then only you can define what your users can access it. Yeah. 32 Gbps is a fair enough assumption to start, because most intra data center high throughput network are 32 Gbps.
Got it. Okay.
Right?
Thanks.
Sure. Super. Gaurav.
Here, let's say, so is each partition assigned one rack, or can one partition have multiple racks? I think one partition have multiple.
One partition is small enough to be part of one rack. But it can still span. It can still span multiple racks. There is no limit to that. because a partition is a logical partition of range, is a range-based partition. So what if I write a new file in that range, which is now going to another rack? So partition can span multiple racks, which is where a defragmentation comes in. It tries to, if it digresses to multiple rack, periodically it would come back to single rack.
And will each vendor be given one whole rack? Let's say
No. That's very inefficient. Very inefficient. Imagine if you give one rack to every customer.
Yeah.
And they don't use it. They just put
Isolation
one
fail
file
at
and they
that
forget.
place? Won't our vendor isolation fail at that place, or we just live with it?
But it's small thing, right? When a bucket becomes big enough, then you assign a separate rack to that. That's where you do that migration of data. One-time migration of data for that. But to start with, you would start multiplexing them. Once a certain thing grows beyond a certain scale, let's say more than 500 GB, let's say that's your threshold. Once a customer crosses 500 GB in a bucket, then you assign a separate rack for that bucket. Right? But that too, not separate rack, but you move it into a separate sense, because you would have some buckets which contain small enough data. Everyone starts there and then moves to that other part. Right? But it still does not mean that one customer gets this one entire rack. That would never happen, because then AWS margin would drop down.
And I have one quick question on CDC. Can I ask it right now, sir?
Yeah, go on.
So is the data replication done through CDC itself? Let's say we use master slave architecture for our databases. Is that done via CDC?
Kind of, yes. Because true for some databases, false for other databases.
Okay.
Because in some cases where database does not have bin log files or commit log files, then CDCs will iterate in the rows explicitly. While if some database gives you bin log file, replication, the default replication leverages those bin log file and commit log file to do the replication. Right? So CDCs is superset of replication.
Okay.
Right? So typically the way replication happens is by reading the bin log file and commit log file from the master on the replica. Yeah.
And a normal informative note that one bucket name cannot be used by any other accounts.
Yes. Bucket names are unique.
Yeah. Like I didn't know that it was all over the world, all over the whole.
No, all over the world it's unique. Bucket names are unique.
Yeah. Thanks.
Yeah. Anubhav?
Here, Pit. So I was following the discussion around chunking and around read. That since our system is not read heavy, we should not, like, chunking does not make much sense. But what about, since our system is write heavy, do you think chunking makes sense for parallelizing writes?
So long as user sends you parallel writes. If user is not sending you parallel writes, you can't do much. Correct? If let's say your chunk size is 128 MB, user is not sending you parallel, user is sending you sequential writes, you cannot leverage that. Correct?
Yes, that's right.
So you are assuming that user sends you parallel writes, which you can accept and then write in parallel. Then you can leverage it. And these are supplements to the core feature. And which is where here when we talked about it, that your physical limit might be 1 GB, but your logical limit of a file can be 1000 GB, because you are implicitly chunking and storing that meta information internally. And then you can leverage it. Right?
Yeah. So to close the loop on that, by user, like our client code should support that functionality, offer that as a feature to be able to got it.
Correct. So if it can send you in parallel, you can accept in parallel, then good enough. But then you are risking your random writes on your storage side. So be wary of the fact that their random writes would come in. And random writes, but because they would be close enough, so the head movement will not be massive. It would be a little bit, but it's still enough that your throughput would go down on the storage layer.
Yeah, makes sense.
Right? And now crunching numbers on this part is always putting load and seeing how your system reacts. Like, because unless we have built it, unless we have seen it, we cannot comment on it. So the way I would have done it is I would have built a system on a storage, and I would have actually monitored those metrics on how it is behaving, and then come up with that numbers. How, like, if what all features would I need to support? How much throughput would I be able to handle? Is it good enough benefit or not? And then we would take a call to release that feature.
So for a quick follow-up on that, is it like possible to prototype this locally on our machine, like treating
Yes,
our
just buy a if you have SSDs, you will not see that big of a difference. But if you have hard disk, magnetic disk storage, you can do that. But apart from this, you can anyway prototype S3 very easily. You want to implement chunking, you can implement chunking. Storing file, you just store it on local hard disk path, store that mapping, store that partition mapping and whatnot. You can very well mimic it. Very well. It's not difficult to mimic. Obviously, scale is different, but at least writing that hello world of S3, you can very well do that.
Yeah.
1 month project, but if you'll have much deeper understanding post that, right? What gets stored in partition map table? How are you moving data? How is merge and compaction happening? Whatnot. You can mimic all of that locally.
This is something I want to also try out. Like very curious.
1 month of time, go for it, man. Go for it. Take 1 month.
Yep.
Siddesh. Yeah, thanks, Siddesh.
Hey, Arpit. So I was just thinking when you were having discussion on that numbers. So I just wanted to this HDD is not that fast, right? It's not that. Did you say like I was just understanding like with 5 milliseconds to 10 milliseconds latency, right? It can't go beyond 500 Mbps.
Yeah. I'm giving 32 Mbps, like 32 Gbps as a starting point.
Oh,
and
I see.
It drops down below that because, and why 32 Gbps? Because 32 makes calculation very easy.
Got it.
Then the only parameter you need to change is that 32, like that part.
No.
Because
I did not know that was a random number. It's fine.
No. It's by the way, it's not very random. 32 Gbps is the maximum that a intra data center network can support.
Yes, I was going to get there.
So
I was
the max. That's the max that you can get, right? Which means if you change your hard disk to the fastest one, this will become the bottleneck. This 32 Gbps, right? This is what I started with. That now today it's HDD. Tomorrow, let's say you get the fastest hard disk out there, or let's say you store it in RAM. Right? Your RAM can give you much faster than that, but you're still bottlenecked by your network, which can send at max 32 Gbps. That's why I started with that. It's not random number. It's the max. It's the physical limit of the connected network of the connecting network cable in your data center. It's that limit. So no matter now, I'm not just restricting it to HDDs. Take SSDs, take RAM, take L1 cache. Let's have a distributed L1 cache, the fastest that you can. But you're still bottlenecked by this 32 Gbps, right? So if you start with this assumption, change the underlying storage to as fast as you can, but you cannot go beyond 32 Gbps. It just falls back everything, right? So you start with that, and then you just change this number to see, okay, now I can get much less than this, right? That's right.
And that's a good insight because if we are designing a storage system, our bottleneck should be storage, not network.
Yeah, exactly. Yes.
Another question I had on the same line was that if we do those calculations right now, the hard disk is fine, like 500 Mbps. Now let's go to the network. Can you go to the diagram, the high level diagram that you have?
Yeah,
this one.
The
high level, yes, here.
This one.
So now our data hop is going to be most probably API to partition server to the rack, right?
API to partition server to rack, correct.
Yeah. Now our API server, let us suppose how many, now the limit is going to be what I was trying to get to calculate those numbers that it is going to be the API server because partition server also has lesser requests.
Correct.
The throughput that needs to be delivered by the API server, and client side is fine because there could be multiple clients. Over the internet it could be less, but at the end of the day our APIs. So basically I'm assuming the reason we are doing all of this is the network cables attached to rack, to partition, to API are heavily mostly optics, but the control plane can be normal network, right?
Yes.
That is
yes.
Okay. Yeah. So that I
This
think your
needs to be
discussion helped
lightning
me
fast.
understand this.
Yes, this needs to be lightning fast. If this is lightning fast, this would be very fast. This you cannot control, but whatever is within the data center, you can assume that it's best is basically best out there, right? And then you build on top of. But
that made a lot of sense to me because in terms of it's very difficult to design this in terms of. So my another question was going to be, you remember the Instagram discussion we had?
Yeah.
We directly uploaded it through that. So my question was like in terms of security and all of this, how is this handled? Because if you through the data, now how do you make sure that you are still guaranteeing the public cloud security and still your data, like you'll have to expose at like minimum servers out to the public, right? That's where I'm confused here. Like most probably like our control plane requests were fine. We could go through DNS and all of like all the proxies and authentication servers and everything. But how do you make sure someone who is pushing data can be authenticated on every request?
Okay, that is where the S3 signed URL that we're talking about, the signed URL is nothing but a certificate. So when you get a request like that, you just validate the certificate over here. You don't need to make a database call. It's just a validation of certificate, right? You just do a quick validation of certificate, basically decrypt it and check the validity, check if the signature matches or not. Once you do that, that's good enough for you to let the request go through the partition server and whatnot. So
I see. I mean, I can still think of hacks for man in the middle for this, but
no, the private key is with the customer. You can only validate a certificate.
Perfect. Okay, it's not just the link; it's the whole private key, right? So the
private key is the customer to do that. So it's part of the SDK that it ships with. So private key is with the customer to basically do that, and it's very short-lived. So someone having that, it would be very difficult to bypass it. So that's the signature that we go with.
Got it. And another point I wanted to ask you is, which maybe we have not covered it. Like it's fine to ignore the question if you're going to cover it later. But about compression and encryption, the things like this. Now, I like when we were discussing this hot, cold, warm storage. How does compression, encryption, and those things play in the picture? Because one normal question I had was when we had this whole data engineering pipeline. I was assuming when you do joins and like basically if you're doing in JSON formats, you're duplicating data now. So your warm storage is going to have a larger space than your hot storage, and same goes for cold. But it's fine. Like it's about cost and queryable form.
Correct. The compression thing you talk about will not go for out of the box compression. The format that we typically go for is a columnar format when we store this data, right?
Okay.
That format, for example, Parquet, if we use Parquet, natively compresses the data and stores it.
I see.
You leverage the format that gives you those things out of the box. You don't rely on compression done by S3. It typically does not do any compression there, right? You rely on your side. The format in which you are writing to the staging S3 can be a columnar format like Parquet, which internally compresses the data and stores it.
That makes sense. Okay. Yeah, because now this whole public cloud thing, I'm also assuming that the whole data that resides on any of those disks are encrypted. Because now such huge data has also CPU overhead. So these API servers which are going to do this, it's not just network and disk now. Because
now it's CPU bound as well. And encryption is very common. For every bucket that you create on S3, you can provide a custom encryption key.
Exactly. Yeah, that's the trickiest part, right?
Yeah. So decryption, decoding, and then sending it to the user. encryption, encoding, and storing it on storage. Yeah.
Right. And I was reading about S3 throughput. It seems like they can give GBPS and that's where I was wondering, like giving GBPS.
Now I told you.
Now it definitely means. What I'm thinking is it definitely means they are doing parallel writes, because that cannot come through a single disk.
Correct. So it is also possible that they accept the writes, but then write it asynchronous way.
Oh, okay.
That is also possible, yes. Right?
That's also
right.
Possible.
They can also chunk and do it. So it's more about how quickly they can accept the writes.
Right.
Rather than
there may be tiering as well. Maybe there are SSDs sitting in front of it.
Yeah. There are so many complexities that are involved. So depending on how S3, because S3 has now basically 15 years of evolution. They started with something, with time progressing, they are making changes to their features and all. There will be tons that would be coming, and it's not as simple as I do. But you get this idea now. You can think.
I'm discussing just for the same sake, like to get the general idea of things, right? Like because once you try to tweak one, there are 3 things that come out which are problems.
Yes.
Anyways, thank you. Thanks.
Yeah, thanks. Yeah, Rajiv, go on.
For multi-tier storage, if you can go to the diagram.
And open that.
Data pipeline is something which I wanted to know what, I am not very familiar about that.
I'll explain now what data pipeline is. You want to know about data pipeline?
Yes, yeah.
Okay.
Why it is used.
Okay. Data pipeline is a term that people use, which calls it, we take data from one place, put it into another. In reality, it is just a Spark job which is running, which is reading data from one place and putting it into another. The process is called as pipeline. It does not mean we are automatically fetching it or putting it there. It's literally a Spark job that you write a query that you need to fire on this database. You write a query through which you would want to store this into this database, and a Spark job runs and does that for you. That is what a data pipeline is. Data pipeline is basically a simple process that reads data from one place, modifies data in some other, basically transforms the data and puts it into different ways. That is ETL, extract, transform, and load. That's what our ETL pipeline or data pipeline is all about.
Throughput also increases like multiple reads, transforms.
That is features. That depends on how you write your Spark job. Throughput, parallelism, whatever you want to get it. That is how you write your Spark job. But a core idea is you extract, you transform, and you load.
Okay, understood.
Right. So whenever someone says data pipeline, it's literally something, a process that connects two data sources, takes data from one place, applies some transformation, stores it up.
Yeah, I mean, Spark job, I mean, I have read about MapReduce and all those things. So Spark job is similar to MapReduce, or how they are linked?
Spark job is similar to MapReduce. Like, that's a oversimplified. Yeah, Spark job is similar to MapReduce, where it distributes the load across multiple machines. It does that cluster management for you.
Yeah, map and reduce.
It does distributed computing for you. MapReduce is different. Spark is different. Spark does it in memory. It still moves the data across, basically shuffles the data and whatnot. But it basically abstracts out distributed computation for you. For example, if you're reading 1 terabyte big table, one node will not be able to process that much of data. Let's say you're reading 2 tables, joining them, both tables are 2 terabytes. 2 terabytes RAM you have on your machine? No. You need to distribute it, right? So the way the job would be distributed, each server would pick up a small fragment of data from this table, would join it and put it there. This sort of distributed computation, and then some job would take all of them and basically combine it and then serve it and then load it into another data. This abstraction is done by Spark.
Okay.
The distributed computing part, Spark takes care of that.
I want to read more about this. I mean, any good resource you can.
O'Reilly book on Spark is good one.
Okay, you told once, yeah.
Yeah, that one. I put the link in Discord as well. In Feb 2023 cohort, I put the link in. I think it's called Effective Spark or something. I read that to build an understanding. Yeah. That's a good place.
Yeah, one book was there. Yes, I saw. Yeah, okay.
Yeah, that's the one. I referred that. And more importantly, don't just read, code it out. Unless you code it out, you would have no idea what's happening. So code it out to get a deeper understanding.
Okay, sure.
It's fun. The world of data engineering is very interesting.
Cold storage by default is S3, right? I mean, when you say cold storage is S3,
most
permanently
probably
down.
S3 or any blob storage.
You mentioned the term glacier also, right? So what is glacier here?
In S3, there is multiple tiers. In S3, there is an infrequent, there is a standard tier, there's an infrequent access, and there is a glacier tier. So it's one is more cheaper than the other. Glacier is the cheapest one. It gives you very slow reads as compared to standard tier. Infrequent access is in middle, and glacier is even slower than that.
And you also have a policies for that as well, where you want to put
where you move it. So on S3, you can configure that. I'm so happy you are listening.
I just try to make note. I mean, it's very difficult to remember all those things. Such three along.
What to do, man? System design is very vast. We can't help.
I mean, you are on the flow, right? And I have some questions. So it's very difficult to go back to I don't write questions. I just listen, because if I write question, I just break the flow of my listening, right? So here is the, gap which is there. I have to write things, but
yeah, you should write. You should take notes always. Like at your job also, just keep taking notes. It does not mean descriptive notes, even a word, even a small question, even a small concept, just make a note of it. It's very helpful. So that you don't have to put all things in your cache. You're flushing it onto a disk and reading it from there. Yeah. God, fine. Chalo, great. Thanks. Anyone else? Any other question? No. How many survived? 11 folks. Superb, including me. 10 folks survived. Thanks so much. It's quite late, 12:45 already. But I hope you found this discussion amusing. I tried my best to cover it in depth, answer all the questions. But in case there is any, feel free to ask me anytime in the course, one-on-ones on Discord, wherever. More than happy to answer them. Right? I'll upload the recording by evening. Thanks so much.
One thing more, Arpit. Let's say after the course is over, 1 of the months also over. If you want to ask, and then
Discord is the way. Discord or email. Yeah, asynchronous.
Yeah.
Right. Super. Thanks, folks. I'll upload the recording by evening. We'll see you tomorrow. Bye bye.